Thank you, Shumaila. So, good morning to all of you. Once again, I welcome you. And today we are at the fourth day of this GIAN program on fascinating features of nanodimensional smart materials. And I'm your course coordinator. I'll be taking you to the world of electrochemical studies, the voltammetry and amperometric technique, which are mainly used for and which I am going to talk of is energy storage devices and the sensor. The application of techniques like voltammetry and amperometry in energy storage and sensing. Before moving on to electrochemical technique, let me introduce you with Alessandro Volta. He's a scientist who developed the world's first battery in the year 1800 by placing sheets of zinc and copper electrodes by stacking them, and in between them he placed cloth immersed in an electrolyte. That cotton cloth immersed in an electrolyte basically serves as a medium for transfer of ions, and that assembly produces electric current for the very first time. And his surname Volta has become the unit of voltage, capital V, represented with capital V. There were few other scientists who have contributed greatly in the field of electrochemistry. One of the scientists was Michael Faraday. He worked in the area of electricity and electrochemistry and the chemical reactions and how electricity influences a chemical reaction. And you must be aware of the two very famous laws of electrolysis given by Faraday. He discovered the principle of electromagnetic induction. Now, what is electromagnetic induction? Earlier, it was believed that these two forces are different forces. The electric force is a different force, while a magnetic force is a different force. But later it was realized that they are not different forces, they are same forces, because whenever you have an electric current, it creates its magnetic field. And if you have a magnet, you take a coil, pass the magnet through that coil, it creates an electric current. So whenever we have magnetic field, it creates electric current, and vice versa is also correct. Do you have any idea about how many fundamental forces are there in the universe? Anyway, just to make this discussion more interactive, I think I should ask some minor questions. Even the online people can also answer. How many fundamental forces are there in nature? Any idea? Any guesses? Four of good. There are four fundamental forces of nature. Can you name those forces? Gravity is the right answer. Electromagnetic force, yes, the right answer. There are two more forces. These forces are running the universe actually. There are two more forces. One is called as the strong nuclear force and weak force. The strong force and the weak force. The strong force holds the protons having same charge inside the nuclei. It is so strong that even same charge particles having very high repulsion, they can stay together. They can stick together with the help of this force. And the weak force is because of which a nucleus emit alpha and beta particles to stabilize itself. That is the weak force. A strong force is among these all these forces, it is the strongest, but its influence, it influence only for a short distance only. While gravity, although it can be experienced even for long distances, even we are facing gravity on earth, and different planets, even black holes have very high gravity. So gravity, although can be experienced even at a long distances, but it is considered as weak force, because if it is very strong force, we won't be able to move, we won't be able to jump. So these are the four different forces. Earlier the electric and magnetic forces have been considered differently, but now since they all have and they have a vice versa effect, electric field creates magnetic field and magnetic field creates electric field, so they are considered same force. So Faraday explained how when electricity is passed through a solution, how the metals are being reduced and they are being deposited on the electrodes, and he has given two different laws. Then there was another scientist who is famous for wireless electricity transmission. His name is Nikola Tesla. He was working on the development of alternating current and electricity transmission. The coil developed by Tesla, it is still used in radio communication. It basically consists of two different coils kept at a distance. Both these coils have capacitors. One of the capacitor charges the coil, the current is generated, which creates a magnetic field, and and spark is created. With the help of that spark, electricity magnetic field is transferred to the other coil, and with the help of that magnetic field, an electric current is created in the other coil as well. So with the help of his invention, we can transfer that electricity with the help of magnetic effect to the other coil. So let us talk briefly about nanomaterials. Since this course is of fascinating features of nano-dimensional materials, so all materials which have at least one dimension in the range 1 to 100 nanometers, they are called as nanomaterials, and they are used in medicine, electronics, biotechnology, energy, environment, and numerous fields. Do you have any idea about what are zero-dimensional materials? Even Professor Sapra was also telling, yes. Zero-dimensional materials means they do not have any, they cannot move freely in any dimensions. All they are trapped. Yes. No. So therefore they are trapped inside. So like quantum dots or some other type of nanoparticles, they where with which cannot move freely, they are called as zero-dimensional materials. You must be aware of all these. And then we have one-dimensional materials. So one-dimensional material are those which have one dimension. In one dimension, they can move freely. Examples are carbon nanotubes. Then we have nanowires, nanorods, etc. Then we have two-dimensional nanomaterials which can move in two different dimensions. Examples: graphene, magazines, and various other metallic nanoparticles like molybdenum sulfide, disulfide. Why is this not working? And then we have three-dimensional nanoparticles which can move in all three dimensions, like the bulk material. But those bulk material have characteristics of nanoparticles, like they have either the pore size of nano range, they are like nanocomposites, aerogels, dendrimers, etc. Now, as you all know that because of very high surface area, as we keep on reducing the size of a material, the surface area increases, the surface to volume ratio increases, and most of the properties, most of the application of a material are basically based on their surface, because when we are doing a reaction, it is the surface which is involved. So if higher the surface area, more free will be there. The properties shown are even more pronounced because of their very high surface area. So these nanoparticles have high conductivity, large surface to volume ratio. They are also used for surface plasmon resonance and like in electronics and optical applications. And they have very good electrocatalytic properties or in electrochemical properties as well. And therefore, because of those properties only, they are used in energy storage and sensing applications. Now, let us move on to electrochemical methods. Electrochemical methods are those methods which involves the principles of electrochemistry. And electrochemistry principles, as I told you, I think yesterday also, that the electrochemical reactions are those reactions in which the electrons are being transferred from a material to the electrode and from electrode to the material. Means the electrodes and electrolytic and an external circuit is involved in these reactions. One of the substrate undergo oxidation, the other undergoes reduction, and in this way the electrons that flows from one side to other, it creates an electric field or electric current. The two main applications or the two main methods that comes under the category of electrochemical methods are voltammetry and amperometry. that I'm going to discuss in detail. So what is voltammetry? Can anybody tell me what is voltammetry? I told you on day one as well. Any idea about voltammetry? In voltammetry, we give a variable potential to a system and then we measure the corresponding current. So we are giving variable potentials. So potential is also variable, which is an input, while the output is current and the graph is I versus V. Current versus potential graph is the output of an voltammetric system, voltammetric studies. On the other hand, in case of amperometry, what do is we keep the potential fixed, and at that fixed potential, we measure the current of a system with respect to time. So the output graph of an amperometric system is I versus T at a constant, at a fixed voltage. This is the classification of electrochemical methods. Broadly, they are divided into two categories, the static techniques and the dynamic techniques. In case of static techniques, we have potentiometry. Potentiometry refers to the measurement of potential, but not the voltage actually. Most of the time, we synonymously use the word electromotive force and voltage. Do you think they are really same? No, not at all. Electromotive force is the voltage of the system when no current is being drawn from the system. The moment we draw current from the system, now the difference between its electrode's potential is called as the potential difference or the voltage. It is not the electromotive force. So electromotive force, which is also called as open cell voltage or open cell potential, can only be obtained by an indirect method which is called as potentiometry. So potentiometry is a method for measuring the open cell potential or the electromotive force of the system by introducing a standard Wetson cell. I think you might have heard the name of standard cell whose potential remains constant irrespective of the temperature. Means the cell potential does not depend upon the temperature. So that standard cell is used to calculate, to determine the potential of a cell or a system without drawing any current. So if we, for example, if I give you a cell and I ask you to measure the electromotive force, you have a voltmeter, you connect the voltmeter, tell me the voltage. Sir, this is the voltage reading in the voltmeter, so this is the open cell potential or the electromotive force. No, that is the potential difference between the two electrodes. That is not the electromotive force, because when you connected the voltmeter draws current from the cell. So the value goes down. It is not the actual electromotive force. Electromotive force or the open cell potential can be measured by an indirect method by using a standard Western cell and making a circuit, which I think I should explain some other time, and some of the student I think I have explained in class that it is an indirect method. So potentiometry is for measuring the potential without drawing the current. Now in the dynamic techniques of electrochemical uh, methods, we have two options. We have two classes. Either we can control the potential or we can control the current. If we control the potential, again, we have two options. We can either fix the potential at a particular value or we can vary the potential. If the potential is fixed, you can see here, in case of control potential, if the potential is fixed, what do we get? Amperometry. While if the potential is variable, not valuable, it is variable, then there are again two conditions. If we are stirring the solution, yesterday I told you that if we are stirring the solution, we are mixing the solution, so we are giving rise to a new mode of mass transfer which is called as convection. There are three modes of mass transfer I told you yesterday. First is the diffusion, second is the convection, and third is the migration. When we apply potential to an electrode, opposite charge, the charged particles move to the opposite electrode. That is called as migration. So There are two possibilities when we are changing the potential. Either the solution is stirred. If the solution is stirred, the two voltammetric studies are called as hydrodynamic voltammetry or stripping voltammetry. On the other hand, if the conditions are quiescent, we are not stirring it, there are few other techniques, linear potential, then we have another type of stirring voltammetry technique, then pulse voltammetry and cyclic voltammetry techniques. In cyclic voltammetry also, we do not stir the solution. We do not mix the solution, which means that in case of cyclic voltammetry also, there is no convection mode of mass transfer. These three mass transfer modes are very important for electrochemical studies. So this is the basic classification of electrochemical methods. Now before starting the voltammetry or amperometry technique, I should first explain you the difference between resistance and impedance. Resistance basically generates from a resistive circuit only. While if we have capacitive circuit or a circuit containing capacitor as well as inductor as well as resistance, then the sum of all these obstructions will be the impedance of the circuit. So impedance means you are already covering the resistance and you are also using some other types of obstructions in the flow of current. That obstructions comes under the category of reactance. So impedance means resistance plus reactance. The reactance is not significant in a direct DC circuit, but in case of AC circuit, the reactance is very significant and you have to consider it. So while considering the total resistance, we use the word impedance for an AC circuit. Clear? So both the terms, resistance as well as impedance, they are basically obstruction in the flow of current. That's it. And since they are obstructions, the unit is also same ohm. While resistance is mainly studied in DC circuits, we study impedance in case of alternating current circuits, where the current is changing its positions. Resistance is mainly pure, it is a pure quantity. It is only a real quantity, while impedance involves real as well as imaginary part. Impedance, as I told you earlier, that it is even a more comprehensive term. If you are considering impedance, you are considering all sorts of obstructions, all types of hindrances in the flow of current. So reactance basically, resistance basically is the dissipation of energy, while reactance involves the storage as well as release of energy. So it is, if you are talking of impedance, that means you are considering energy dissipation, energy storage, energy release, all sorts of resistances. This is, this way you can see that the impedance becomes very high because it involves, along with the resistance, you have reactance as well. And the impedance is calculated with by just like a Pythagoras relationship. The impedance square, Z square, it is denoted by Z, is equal to the R square plus X square. R is the resistance and X is the reactance of the circuit. Again, since it is a Pythagoras relationship, so again the unit will be same, the ohm. Now depending upon whether we have more of a reactive circuit or more of a resistive circuit. For example, if in a circuit we have more resistive load, then we can say that it is more of a resistance circuit. While on the other hand, if a circuit has more of a reactive load or an inductive load or a capacitive load, we can say that it is more of a impedance type. If either of the component value is large, is a larger magnitude than the other, जो भी ज़्यादा होगा, if resistive load is high, we can call it that it is a type of resistive circuit. Otherwise, if it is a type of a reactive circuit, it considers both these parameters. Now, as you all know that in case of voltammetry, we have two techniques. We have many techniques, but these are the two common, LSV and cyclic voltammetry. So voltammetry refers to the measurement of current produced in a system against a variable applied voltage. And it is of two types. On the other hand, amperometry refers to the measurement of current against a fixed voltage. These are the duck-shaped curve for ideal systems. So voltammetry is basically a time-dependent potential excitation signal is given to the, of course, to the working electrode, because the working electrode is the main electrode where the analyte is either oxidizing or reducing. So we are mainly concerned with the analyte. Analyte is called as the compound of interest. So working electrode is mainly responsible for the oxidation or reduction of the compound of interest. So a time dependent means we have to first of all select the range, as we have shown you yesterday. We have to select the range, that what range of potential we are going to cover it, and at what scan rate. For example, if it is changing from 0 to plus 1 volt, then at what rate is it changing? For every second, either it will go up by 100 millivolts, or maybe by 50 millivolts, or even by 5 millivolts. We have to select that scan rate also. Sorry. Now, when the voltammetric techniques was discovered, was developed for the first time, the very first technique of voltammetry that was developed, it was developed by Jaroslav Herosky in the year 1920, and that technique is called as polarography. So, polarography is also a sort of a voltammetric technique, but in case of polarography, we use mercury electrodes as a working electrode. He got Nobel Prize also in 1959. We use mercury electrode in polarography, and there are three types of mercury electrode possible. These are the three electrodes. The first is called as the hanging mercury drop electrode, HMDE. In this electrode, we have a capillary tube, we have a mercury filled over here, and there is a screw. We rotate the screw, it pushes the mercury forward, the mercury will form a drop. When we push, when we rotate the screw more, it will pushes the mercury, the drop becomes heavy and it falls due to gravity. Therefore, it is called as hanging mercury drop electrode. As long as the size of the drop remains small, it is stay hanging. When the size becomes big, it falls off the electrode. Then we have a dropping mercury electrode. In case of dropping mercury electrode, we are not using the term hanging because it is an open system. We have a reservoir of mercury, liquid mercury, and it is connected to a capillary. It moves down, the drops comes out, the size of the drop increases, and a moment will come when it becomes heavy enough to fall of this electrode. When it fell down, it is immediately replaced with a new drop. It is like a one electrode is being replaced with a new one. Then we have a static mercury drop electrode. In case of static mercury drop electrode, we use solenoid valves. Solenoid valves are basically time dependent valve. You can set the timer, you can close the valve at a particular time that you have predetermined. The valve will open, required amount of mercury is allowed to pass to form the drop and fall off. So it is called as static because here it is static unless and until the valve opens and the mercury moves down. So these are the three types of electrodes which are used, and while using this polarography, the very famous equation which is used to calculate the diffusion current is called as Ilkovic equation. ID is the diffusion current and it is equal to 607 NCM to the power 2 by 3 T to the power 1 by 6 under root D. ID is the diffusion current in microamperes. 607 is a constant value that is basically dependent on various factors, including the Faraday constant, the density of Hg, the conditions of those experiment, temperature, etc. N is the number of electrons involved in the electrode reaction. D is the diffusion coefficient in centimeter square per second. how fast the material is diffusing, the ions are diffusing from one place, from bulk of the solution towards the electrode. गिलास होगा यहाँ पे? गिलास होगा? थोड़ा सा बताना था मुझे, शीशे का गिलास मिल जाता तो बता सकते हैं. M is the mass of Hg flowing through the capillary, milligrams per second. T is the time in seconds, and C is the concentration. So with this, you can calculate the diffusion current using the mercury electrode. Now, why do we prefer Hg electrode? Why do we prefer mercury electrode in polarography? Because one of the advantage of mercury electrode is that it can be easily mixed with any metal to form an amalgam. For zinc, copper, other electrodes, it is not possible to mix them very easily. But with mercury, you can mix them, you can form an amalgam very easily. The other thing is that there is a term called as overpotential. Overpotential is basically the difference in the potential between the theoretical value of a certain reaction. For example, there is a reaction. For that reaction, the theoretical value of potential is, for example, 1 volt. But practically, you have to give 1.5 volt to carry out that reaction. So the difference between these two, 1.5 and 1, the 0.5 volt, it is basically the overpotential. Like Professor Sapra has said yesterday that hydrogen is evolved by the reduction of H ion at 0 volt. But if we have zinc electrode there, the same reaction will occur at 0.76 volt. So that is the overpotential for zinc electrode. So if we are using zinc electrode, the H ions, because it's for it, the zinc electrode, it is minus 0.76, which can be very easily achieved. If you are doing a reaction with zinc or a copper electrode, it will immediately forms hydrogen gas. But if you are using mercury electrode, for mercury the potential is plus 0.07, plus 0.70 volts, which is in plus direction. Plus or minus is only the direction. Minus means it is, the voltage can never be in minus. Minus means the voltage is lesser than a reference value. For example, 0.7 minus 0.7 means there is a reference value and the potential is zero point 0.7 volts lesser than that reference value. On the other hand, if you have plus 1 volt, that means from a reference value, it is plus 1 volt. Clear? So for mercury electrode, the overpotential is plus 0.70 and therefore it is difficult. While in case of zinc, it is minus 0.76, which can be very easily achieved, and hydrogen is start evolving during the process. Therefore, we avoid those electrodes and we prefer hydrogen because it has a high overpotential for this particular reaction. And overpotential is basically, write down the difference between the theoretical and the experimental voltage for a particular reaction. So this is the first reason, that it has a high overpotential, so it prevents release or evolution of hydrogen gas. The second reason, it forms amalgam. And third reason, the mercury, because of its liquid nature, it renew itself every time. As I told you, in case of hanging mercury, you move the screw, drop becomes bigger, falls off. In case of dropping mercury, there is no control, it will continuously, drops will fall off and new drops will come. In case of a static electrode, although it is static, but if you have fixed the timer, and once the time is, once the timer opens, the mercury drops falls off, replaced with a new drop. So it renews itself. Therefore, it is preferred. Again, the 2 and 3 electrode systems. I think you're already aware of these two systems. Earlier we use 2 electrode system. We have working electrode and counter electrode now. But if you are using 2 electrodes, it is called as the full electrode system or the full cell system, and it will give you the potential difference between the 2 electrodes, main electrodes. But if you want to study the behavior of working electrode only, then you have to place a third electrode. And then with respect to that third electrode, you can study the potential or the electrochemical behavior of your working electrode. Therefore, we now prefer to use a 3 electrode system in which we have a working electrode, we have a reference electrode, and we have a counter electrode. We connect reference and counter to one terminal and working to the other terminal. Already discussed. Now, Faradaic and non-Faradaic currents. I told you yesterday. Can anybody tell me what are Faradaic current? What is a Faradaic current and what is a non-Faradaic current? Or what is a Faradaic process? A Faradaic process produces Faradaic current. A non-Faradaic process produces non-Faradaic current. So, what is a Faradaic process? Redox reaction. For example, you have an analyte. The analyte is oxidizing, releasing electrons. Those electrons are taken up by the electrode. Now they are circulating through the external circuit. The current generated in this way is called as a Faradaic current because it is obtained by a Faradaic process. It is obtained by an electrochemical reaction where the analyte undergoes oxidation. Clear? On the other hand, if current is generated by a non-Faradaic process. Now, what is a non-Faradaic process? Suppose you have a system, you have 2 electrodes and some electrolyte in it. Now, you have changed the potential of one of the electrodes suddenly, making it a little bit more positive. आपने out of the 2 electrodes in the system, एक electrode का you have given some potential by some external source. एक बैटरी लगा के आपने potential दिया और उस electrode का potential, that electrode acquires a positive charge. The moment it acquires positive charge, now in solution we have, the solution is neutral, we have anions as well as cations. Since the electrode now suddenly after giving the potential, it has acquired a positive charge, all positive ions, all cations start moving from away from each other, from this particular electrode, while all the negative ions which are present into the solution, they start moving towards this electrode, and because of this movement of ions, current is being generated. But here, no redox reaction is taking place. None of the ion is oxidizing or reducing. Therefore, it is a non-Faradaic phenomena, and the current generated by this phenomena is called as a non-Faradaic current. Clear? It is not following the Faraday's law, while the former it was following the Faraday's law. The current which is generated by this sort of non-Faradaic process is called as a, although it is a non-Faradaic current, but it is also called as a charging current. Why? Because this current, this transient current is generated just after giving a charge to a particular electrode. As I just mentioned that if you have given sudden charge, a positive charge, so positive charge moves away, negative charge moves towards that electrode, current is generated. So if, since this current is being generated by giving charge to an electrode suddenly, therefore it is also called as charging current. So charging current is a type of non-Faradaic current. There is one more term, because I think I should, before starting voltammetry and amperometry, I should explain the basic term so that you may not get confused. There is another term called as residual current. Can anybody tell me any idea about residual current? Those who are sitting at the top? Anyway, the residual current also has two components, the Faradaic component as well as non-Faradaic component. But the current, the Faraday component of residual current is not because of analyte, because if it is because of analyte, it is not called as the residual current. Residual current means that it is not generated because of the redox reaction of analyte, it is not generated because of oxidation or reduction of analyte, it is not generated because of Faradaic process of analyte, it is generated by the Faradaic process of impurities which are present in your system. That's it. And the non-Faradaic component, again, it is because when you give the charging to an electrode, ions moves, current is generated. So residual current is basically the current which is due to the oxidation or reduction of the impurities, as well as if you have given some charge to the electrode due to non-Faradic process. This is called as residual current. And the point to be noted here is that if a Faraday current is generated due to reduction of the analyte, for example, you have an analyte over there, current is coming from the electrode, the electrons are released and that analyte accepted those electrons and undergo reduction. The Faraday current generated due to the reduction of an analyte is called as cathodic current, and its direction, its sign is positive. Write down, this is very important point, most of the students confused. While the Faraday current due to the oxidation of analyte is called as anodic current and its sign is negative. Write down, Faraday current, analyte reduction called as cathodic current, plus sign. Faraday current due to analyte oxidation is called as anodic current, sign is negative. Water bottle. Yeah. Now let us take the example of ferricyanide. You have, for example, ferric ion in solution, Fe plus 3, and you are reducing them to ferrocyan, Fe plus 3 to Fe plus 2 at the working electrode. Suppose initially, since the reaction has not started, you have only Fe plus 3 ions because this reaction is not started yet. For this reaction, the required potential is plus 0.356 volts. Now, when we start the reaction from a positive value, for example, we have given initially plus 1 volt or even plus 0.5 volt, nothing will happen. But as the potential goes down and it reaches to a value plus 0.56 volts, immediately Fe plus 3 start reducing to Fe plus 2. Now, for example, you have a system and you have a working electrode over there, and you have placed some ferric ions into it. Now no ferrous ions are present. You give the potential. Initially the potential value was plus 0.56. Nothing will happen. But as the potential drops and it reaches to plus 0.356, at that particular potential, the ions which are present in the vicinity or which are present at the working electrode, they immediately undergo reduction from Fe plus 3 to Fe plus 2. Now the concentration of Fe plus 3 at the working electrode goes down because all Fe plus 3 has been converted to Fe plus 2. While there are many Fe plus 3 ion in the bulk of the solution. So there will be a concentration difference of Fe plus 3 ion near the electrode, all Fe plus 2 because Fe plus 3 has been reduced to Fe plus 2. On the other hand, we have plenty of Fe plus 3 ion in the bulk of solution. They start moving due to diffusion. This is called as diffusion, the mode of mass transfer. They start moving towards the working electrode. The moment they reach working electrode, they receive sufficient potential and they immediately undergo reduction to form Fe plus 2. This is the reduction reaction where only diffusion is occurring as a mode of mass transfer. Clear? Now a point will come when the concentration of Fe plus 2, since it is going up because of the reduction, while earlier we have 0 Fe plus 2 and we have very high Fe plus 3 because all the ions were of Fe plus 3. As the reaction proceeds, Fe plus 3 goes down because it is reducing into Fe plus 2, while Fe plus 2 goes up. Now a point will come when the concentration becomes equal. Now the diffusion of the ions will stop. No, the current will no longer exist. Current will only exist when there is a concentration difference. Clear? So this sort of movement of ions is called as diffusion. You have to do nothing for diffusion. You don't have to apply any charge. You don't have to mix the solution. It will move on its own just because of the concentration difference. So for example, this is the system खाली बॉटल है, ये गिलास दे दो, पेन दो. For example, if this is the system, you have an electrode, working electrode over there. On the other side, we have a reference electrode. Now we put some Fe plus 3 ions into it. So the concentration of Fe plus 2 at this time is 0. The potential is 0. We have not started the reaction. Now when we start the reaction, we give the potential. Initially the potential value was high. Nothing will happen. As the potential drops down, it reaches to plus 0.356. Immediately the ions which are present at this electrode, or it is near this electrode, they immediately undergo reduction. The moment they undergo reduction, okay, there are two boundaries. One is called as the surface of electrode, the other is called as the bulk of solution. So ion present at the surface of the electrode, they undergo reduction to form a ferrous ion, while the rest of the solution still contains many Fe plus 3 ions. So when the concentration of Fe plus 3 goes down here, while the rest of the solution has, they start moving. They start moving towards the electrode. As soon as they reach to the electrode, they undergo reduction. So the Fe plus 2 keeps on increasing, while Fe plus 3 keeps on decreasing. And the moment when the concentration becomes equal, migration, the diffusion of ions will stop, the current will stop. Again, I just want to explain you the mode of mass transfer. Diffusion we have just covered. It occurs when the concentration of ions or molecule is different at the surface from the bulk of the solution. If we apply potential to completely reduce, जैसे मैंने अभी कहा, more Fe3 will diffuse. जैसे जैसे as soon as the Fe ion near the electrode undergo reduction, more Fe ions will come. जितना ज़्यादा यहाँ से reduce होगा उतना ज़्यादा आएगा. कब तक आता रहेगा? Unless and until the concentration of Fe plus 3 and Fe plus 2 becomes equal. The second type of mass transfer is convection. It is only possible if we are stirring the solution. The result will be different. If diffusion is taking place, the graph will be different. If convection is also taking place, the graph will be different. I'll show you the graph. So from the graph only you will observe, when you do it for your test system, in your research or in master's or undergrad project, just by looking at the graph, you will observe that whether convection is taking place in your system or not, whether migration or diffusion is taking place or not, or whether all the these most mode of mass transfers are taking place. Just like I explained you in case of GCD, that if you are doing GCD, you will first of all identify by looking the graph whether they are EDLC, or if the curves are there, you get to know that they are pseudo capacitive. And from these curve you will identify specific capacitance, then energy density, then power density, and various other parameters. You will also get to know about the cycling stability. You will also get to know about the performance of your cell after 1000 cycles. So from one curve you got many data. Similarly, from the curve you can easily identify about the mode of mass transfers. Then third is the migration. Migration is only possible when you have charges on two electrodes. One is positively charged, one has plus Q charge, for example, the other has minus Q charge, and the ions will move towards the opposite electrode. This sort of movement, or this sort of transfer of ions under the influence of charge is called as migration. The diffusion current for such system, other than polarography, the diffusion current for such system is given by ID is equal to NFAD C bulk minus C X0 upon delta. C bulk means the concentration of analyte. For example, in this particular case, our analyte is Fe plus 3. So the concentration of analyte in the bulk, while the concentration of analyte X0 means at the electrode, at zero distance from the electrode, means at the electrode surface. So the concentration of Fe plus 3 at electrode surface is represented by Cx is equal to 0, while the concentration of Fe plus 3 in the whole of this solution is called as C bulk. N is the number of electrons, again F is the Faraday's constant, A is the area of electrode, D is the diffusion coefficient, while delta is the, can anybody tell me, where is Aditi? Delta is the thickness of diffusion layer. The thickness of the diffusion layer increases as the reaction proceeds. जब जितना diffusion layer thickness means जहां तक diffusion operate हो रहा है, जहां तक diffusion, the distance up to which diffusion is occurring. For example, initially ions are here while the rest of the Fe plus 3 ions are far away. If we are not doing anything, Fe plus 3 will reduce to Fe plus 2. तो सबसे पहले जो the ions which are closer to the electrode, first of all they will come. Then the ions which are farther from electrode, then they will come. And at the last, ions which are at the farthest place from this electrode will also move. So this shows that initially diffusion was taking place was occurring at very short distance. Then the distance of diffusion or the limit of diffusion increases. Then after some times it even increases further. So this shows that diffusion increases with time if no other mode of mass transfer is occurring. If diffusion is the only, write down, if diffusion is the only mode of mass transfer occurring in a system, then the thickness of diffusion layer or the limit of diffusion that increases, that limit increases. बड़ा कंटेनर होगा उसके भी दूर से भी आयन आना शुरू हो जाएंगे, ठीक है, as the reaction proceeds. जी diffusion layer की thickness delta you can identify with the help of these data from the diffusion current, because diffusion layer is in, if the length of or the thickness of diffusion layer is high, then that means diffusion is influencing for at a large, even at a long distance. That means more ions are coming, that means more current will be generated. So this thickness of the layer is proportional to the current, or the current is proportional to the thickness. So with the help of current, if the current ID value is high, that means the thickness of the layer or the delta we can relate it with. Clear? So we can, with the help of current and these parameters, we can calculate the thickness of the diffusion layer delta. So F is the Faraday's constant, A is the area, D is the diffusion coefficient, again C bulk and C x is equal to 0 is the concentration at electrode surface and bulk of the solution, and delta is the thickness of the diffusion layer. The thickness increases as the reaction proceeds. Higher the thickness, lower will be the current, lower the thickness, because they are inversely proportional. You can see in this figure that earlier we have FeCN 6,3 negative, here Fe is in plus 3 state. It is coming towards electrode, and the moment it comes near the electrode, an electron is being given by the electrode. Fe plus 3 accept this electron, immediately form Fe plus 2 and then moves away. In this way, this is type of a shuttling service. From here we are getting plus 3, taking electron, undergo reduction, and the moment it forms Fe plus 2, it moves away from the system. This way diffusion operates. Now, this mode of mass transfer has a strong influence on the shapes of voltammograms. As I said just now, that from the shape of the curve which you obtained, you can identify what kind of mass transfer processes are taking place or not, because they have a strong influence. The two common shapes of voltammograms are like this. Even such shapes are possible in CV as well as LSV. It is only a part of the curve I have shown here. Even in CV also we may get such type of peaks and then a cyclic curve, and even in LSV also, where we have only a line. In that line also we can have this sort of curve. So the shapes of voltammograms depends upon how we measure the current and how the mass transfer is taking place. Suppose convection is also taking place. Convection is occurring as well as diffusion is occurring, both in this particular system. If I say convection is occurring, that means I am stirring this solution. मैं इसको स्टीरिंग कर रहा हूँ, and because of stirring, आप सोचिए थोड़ी देर के लिए convection की बात सोचिए. If I am stirring this solution also, what will happen? The ions which are present near the electrode, Fe plus 3 ions, they will reduce to form Fe plus 2. The moment they form Fe plus 2, the concentration of Fe plus 3 is low here, this side, while all this portion has high concentration. But since we are stirring it, it will immediately stir the solution and make the concentration constant, uniform in the whole of this solution. जब ऐसा होगा, then there will be no, ऐसी कोई situation नहीं आएगी कि एक वक्त में बहुत ज़्यादा that a number of ions undergo reduction at a particular time and we got a peak, because all the time, because of this stirring, the concentration remains uniform. Therefore, instead of a peak, we got this sort of curve. This type of current is called as limiting current. Limiting current IL is only possible when convection is taking place. Write down. Limiting current is possible when convection is taking place, when we are stirring the solution. Because when we are stirring the solution, the concentration remains uniform, and since the concentration remains uniform, there will be no peak like this one. The curves are smooth. Even the current is increasing, it is still quite smooth because the concentration is uniform. जब concentration घट रही होगी तब भी वो यूनिफॉर्म रहेगी. फॉर एग्जाम्पल, इनिशियली इट इज 1 molar concentration of Fe plus 3 ion. Now since some of the Fe plus 3 ions have been reduced to Fe plus 2, now the concentration becomes 0.8. So the whole solution becomes 0.8. It is not that this point has 0.9 while this point has 0.8, while the middle portion has 0.7, and this portion which is very close to the electrode, it is having 0.4. This will occur only when diffusion is taking place. But since convection is also taking place, we are stirring the solution, then all the times the concentration remains uniform. If it is going down, the whole concentration still remains same, 0.8 in the whole solution, then again 0.7, 0.6 and 0.5. It will go down in this fashion, and therefore we do not get any sharp peaks. Even when the current increases, the curve is smooth. This type of curve is, this current is called as limiting current, and it is only possible when convection is also taking place. On the other hand, if convection is absent, if there is no convection, then what will happen? Initially, no current because the system is not started. The moment we start giving potential, some of the ions are getting converted into Fe plus 2. After a certain period of, so the current will go in increasing, and a point will come when the concentration near the electrode is going down and there are no more ions left in the bulk of the solution even to fill it up, fill this gap. So the concentration, the current will go down. This type of current is called as peak current. This is called as limiting current IL. This is called as peak current IP. If you are getting an IP in your curves, this means diffusion is taking place. If you are not getting any sharp peak, you are getting smooth curves. This shows that convection and diffusion both are taking place. Now, how will you determine the concentration of analyte at a particular point? Let us assume the same redox reaction where we have ferric cyanide in which we have Fe plus 3 ions, and now they are reducing to Fe plus 2 ions. Suppose we are stirring the solution also. Let us assume that only Fe3 is present in the bulk of solution and that we are stirring the solution. It is, I am talking out before the start of the reaction, we have Fe plus 3 only and we are stirring the solution. Now when we apply potential, again there will be a reduction of Fe plus 3 to Fe plus 2. The moment it happens, more Fe plus 3 ions are moving for reduction. Again, since we are stirring the solution, the concentration remains same. The current in this case can be given by K naught, the concentration of Fe plus 3 in bulk minus the concentration of Fe plus 3 at X naught. Clear? Ko is equal to NFAD upon delta, because this is the equation. ID is equal to NFAD C bulk minus C x naught upon delta. So we have replaced n FAD upon delta because they all are constant terms. We have replaced n FAD upon delta with K naught, while we keep these two terms because they are now the main terms which we are going to determine. So we have replaced FAD n FAD upon delta with K naught. K naught is n FAD upon delta. It is written over there, and these two are the terms which we are focusing now. When we reach the limiting current value, because since we are, as I said, we are stirring the solution, it is convection taking place, so the curve will be like this one. Now limiting, when we reach the limiting current, means this is the maximum current. Now not, it is not possible to have more current. At this particular point, the concentration of Fe plus 3 and Fe plus 2 are same. So when we are reaching limiting current, this means all the Fe plus 3 ion which is present near the electrode is being oxidized. क्योंकि अगर बचा होता is being reduced, because if it is still left, it would undergo reduction. Current should have some value, but since it is already limiting current, no, the current is not going up. This shows that all the Fe plus 3 ion which is present near the electrode has already been reduced to Fe plus 2. So the concentration of Fe plus 3 at electrode surface is 0. Therefore, Fe plus 3 is 0 at x is equal to 0 means the electrode surface. Now, when we put x, this Fe plus 3 x naught 0, the equation becomes ID is equal to K naught Fe plus 3 bulk only. So, from this, we can easily calculate, if we know the value of IL, K naught, the value of constant is already known, you can easily calculate the concentration of analyte at any point. Clear? So this is what we were discussing in determining concentration. First of all, if convection is taking place, I naught is equal to K naught. If you do not want to put K, you can put directly n FAD upon delta, Fe plus 3 bulk minus Fe plus 3 x naught. And since we have reached the limiting current, that means no more current is being generated. Now all the Fe plus 3 ion which are present at the electrode has already been converted to Fe plus 2. So the concentration of Fe plus 3 at the electrode surface means Fe plus 3 x is equal to 0, it is already 0. We just put it 0. The concentration, the equation becomes I is equal to K naught Fe plus 3 bulk means the concentration of ferric ion in the bulk of the solution, in the whole of the solution. And from the value of current and putting these constant, you can easily determine the concentration of analyte at that particular time. Determining the standard state potential. Again, consider the same equation. The reduction of iron plus 3 from plus 3 state to plus 2. And again, consider that we are stirring the solution. That means that convection is taking place. So according to the Nernst equation, E cell is equal to E0 cell, the standard state. So E0, the standard state, and the condition Fe plus 3 is getting reduced to Fe plus 2 minus 0.059. कहाँ से आता है 2.303 RT upon NF. When we put RT and the value of F and multiply with 2.303, it changes itself into 0.059. 0.059 divided by n, and in the number of electrons. So here in this case also we have one electron only, so n can be replaced. And then we have log products upon reactants concentration. So Fe plus 2 upon Fe plus 3. Okay, whenever we are talking of electrochemical reaction, we always do at the electrode surface, because the portion of the solution which is far off the electrode surface, nothing is happening over there except the diffusion of ions. The reduction or oxidation is only taking place at the electrode surface. रिडक्शन ऑक्सीडेशन जो भी होगा वो इलेक्ट्रोड सरफेस पे होगा. तो हम जब भी इलेक्ट्रोकेमिस्ट्री की बात करेंगे, इलेक्ट्रोकेमिकल रिएक्शन की बात करेंगे, वी ऑलवेज टॉक ऑफ द इलेक्ट्रोड सरफेस. बल्क ऑफ सॉल्यूशन में कुछ भी नहीं हो रहा, सिर्फ इतना हो रहा दैट आयंस आर मूविंग. जैसे जैसे यहाँ कॉन्सेंट्रेशन कम हो रही है, दूसरी तरफ से आयंस उसकी तरफ आ रहे हैं. जो इलेक्ट्रोकेमिकल पार्ट है, जो रिडक्शन ऑक्सीडेशन पार्ट है, वो सिर्फ यहाँ पर होता है. Clear? So we can develop this relation in the form of current as well.
सिंस लिमिटिंग करंट अभी हम लोगों ने कैलकुलेट किया है पिछली क्वेश्चन में, लिमिटिंग करंट के नॉट Fe+3 बल्क ऑफ द सोल्यूशन। ये जो क्वेश्चन था, अभी यहाँ से Fe+3
x नॉट मतलब x इज इक्वल टू 0 निकालेंगे तो आई एल माइनस आई अपॉन के नॉट। थोड़ा सा मैथमेटिक्स है, आई एम श्योर यू कैन ईजिली अंडरस्टैंड। देखिए एक ये इक्वेशन है, एक ये इक्वेशन है और एक ये इक्वेशन है। इफ आई सब्सट्रैक्ट दिस इक्वेशन फ्रॉम दिस इक्वेशन, राइट डाउन ऊपर आई एल के नॉट Fe+3 बल्क और उसमें से सब्सट्रैक्ट कर रहे हैं आई इज इक्वल टू के नॉट Fe+3 बल्क माइनस ब्रैकेट ओपन कर लो तो K3 फिर के आ जाएगा के नॉट Fe+3 x इज इक्वल टू 0। तो क्या क्या कैंसिल आउट हो जाएगा, के नॉट Fe+3 बल्क ऊपर भी है नीचे भी है तो इट विल गेट कैंसल्ड आउट। द फाइनल इक्वेशन विल बी आई एल माइनस आई इज इक्वल टू ये टर्म और ये टर्म कैंसिल हो गया, क्या बचा के नॉट Fe+3 x इज इक्वल टू 0 बाय सिंपल मैथमेटिक्स, जस्ट लाइक वी सब्सट्रैक्ट क्वाड्रेटिक इक्वेशंस। तो वही लिखा है आई एल माइनस आई इज इक्वल टू के नॉट Fe+3 x इज इक्वल टू 0 एंड फ्रॉम देयर Fe+3 x इज इक्वल टू 0 विल बी इक्वल टू आई एल माइनस आई अपॉन के नॉट। उसको we have a similar reaction for reduced species मतलब as well, अगर हम Fe का रिडक्शन करें, रिवर्स कर दें रिएक्शन को, Fe रिड्यूस हो रहा है, Fe+2 से Fe+3 बन रहा है, एक आयंस निकल रहा है Fe+3 बन रहा है, तो उसके लिए भी यही रिएक्शन होगा। वहाँ पे IO था या KO था बिकॉज ऑफ ऑक्सीडेशन, हेयर वी यूज KR, रिडक्शन हो रहा है, I इज इक्वल टू KR Fe+2 बल्क माइनस Fe+2 x इज इक्वल टू 0। क्लियर? अब बट एट द स्टार्ट ऑफ रिडॉक्स रिएक्शन Fe+2 तो एब्सेंट था, बल्क में तो बिल्कुल नहीं था ना, जो भी बना वो इमीडिएटली इलेक्ट्रोड सरफेस पे बना। Then again I is equal to Kr because since there is no Fe+2 ferrous ions in the bulk of the solution, so this Fe+2 bulk will be 0 and I is equal to Kr Fe+2 x naught. So from here Fe+2 x naught will be equal to I upon Kr, I upon Kr, and K is again NFAD upon delta. Don't confuse, Kr is equal to NFAD upon delta. Now substituting the values, because in this equation for calculating the standard state potential, this is known, this is a constant term, n is also 1. What do we need? These are the two concentration terms which we need, Fe+2 concentration near the electrode and Fe+3 concentration near the electrode. Now Fe+3 concentration at electrode we have calculated by this relation using the limiting current, while Fe+2 we have calculated with the help of the reverse reaction where oxidation is taking place, this one. Now putting these two value, Fe+3 x naught यहाँ रखो and Fe+2 x naught put over here, x is equal to, when we put these equation we will get this particular equation, this. Clear? Now if we know the value of current, we can calculate, because KO and KR are constant, depends upon NFAD upon delta, N is 1, this is also known, plus 0.356 volts. Putting the values you can easily calculate the standard state potential if you know the value of current. Clear? Now suppose we replace the current with, for example, we consider that current is equal to half of the limiting current, I is equal to IL by 2. Just put I, just replace I with IL by 2, means the current is half of the limiting current value. The moment you replace I with I by IL by 2, the equation turns out to be this, and the potential, the standard state potential in such a condition is called as half wave potential. I am sure you have heard the word, those who are working research scholars, they must have heard the word half wave potential. So, half wave potential is nothing but the potential when the current is half of the limiting current. When the current is half of the limiting current value, the corresponding current is called as half wave potential. That is it. So, it will lie somewhere here, because it is I versus V graph, it is I current versus potential graph, and this is the limiting current value. इसको आप, if you draw the perpendicular from this y axis, you will know the value of current. For example, here it is 1 ampere, so we will take 0.5 ampere, draw perpendicular in this direction, again in this direction. So, this particular point at which this curve is cutting, the intercept is cutting on x axis, this is called as half wave potential. So, what is the criteria for calculating half wave potential? What is the method? If you have the curve, first of all identify the value of limiting current. कैसे निकालोगे? यहाँ से draw straight line, the intercept cut on y axis is the value of current. Suppose it is, for example, 0.8 milliampere. If 0.8 milliampere is the limiting current, take half of its value, 0.4 milliampere, come at 0.4. At 0.4 again draw a straight line to the curve. The point at which this straight line cut the curve, draw another straight line towards the x axis. Now, this straight line, the point at which this straight line cut the intercept at x axis, this, because this is potential axis, now the point at which it is cutting this potential axis is called as the half wave potential. So, in this way, with the help of the curve only, you can first of all identify the type of mass transfer processes occurring, then you can calculate the limiting current, you can calculate the concentration of the species like the analyte Fe plus 3, you can also calculate Fe plus 2 concentration, and then finally you can be able to determine the potential value, which is called as the half wave potential, by just putting the current equal to half of the limiting current. Now, let us take some linear sweep voltammetry. Varis, just a second. The slides are not changing, I think. I want to escape. इसको 1 मिनट करना है escape मुझे. Just a second. इसको करो ना. हटाओ, escape करना है इसे voltammetry. escape करना है, escape हो गया. शॉर्ट में लिखना. ठंडा पानी नहीं है, ठंडा देखो करो. शाहब सर को कॉल कर बात है ना. थोड़ा सा पानी ठंडा कर दो बस. बाहर अब वो है, अब बस फिर सर ये 11:30 चाय हमसे बोल देना. लगी. How many students are attending online? वो कर दिया, अनम्यूट किया, अनम्यूट किया. I hope you have understood the concept of LSV, voltammetry, amperometry, limiting current, half wave potential during this lecture. Now, let us dive into LSV, the linear sweep voltammetry. Both CV and LSV are influenced by the mode of mass transfer. The nature of the curve will be different depending upon the mass transfers. So let us first see the concentration profile of an species in an unstirred solution. Then we will see for stirred solution. Unstirred solution. First look at this graph, this one. It is in the start of reaction. We only have Fe plus 2, Fe plus 3, no Fe plus 2 is there. So suppose we have a system, इलेक्ट्रोड्स हैं दोनों, एक और इलेक्ट्रोड है और हमने Fe plus 3 ऐड किया इसके अंदर. Suppose we have this system, यहाँ हमने Fe plus 3 ऐड किया है. Now no Fe plus 2 is here because the reaction is not started. As the time passes, we have given some potential. For example, in the initial 0.6 seconds, the potential is around 0.495. Nothing will happen. But as the potential start decreasing, because as it comes closer to 0.356, 0.37, 0.38, the reaction will start and will get formation of plus 2 by the reduction of iron plus 3. Since the potential is not of that particular value, nothing will happen. But as the reaction proceeds, just after double this time, from 0.6 second, it is now 1.392 seconds. The potential again drops to 0.46 and it is coming closer to 0.356. There is a small current flowing in the system. Why? Because Fe plus 3 is now getting slowly reducing into Fe plus 2. So this is the first curve where points at 0.69 second nothing is happening. But as the reaction proceeds, this is the second one, as the potential drops down, some little Fe ions are getting, Fe plus 3 ion are getting reduced to Fe plus 2, a small current is generated. As the reaction proceeds further, the potential is coming down. You can see earlier it was straight line, nothing happening, but now here a small curve. Again, as the time passes, after 2.088 seconds, the curves are even clearly visible. The current value is increasing. These are the two processes, oxidation one side and reduction. Again, you can see as the potential is coming close to 0.356, it is now 0.391. Again, the current values are increasing. And in this, you can see since it has already crossed 0.356, we have high current values. Then, since we are considering an unstirred solution, which means that only migration is taking place, only convection is taking place. No, sir, only diffusion is taking place, because we are not stirring the solution. We are only considering diffusion as a mass transfer. And I told you that in case of diffusion, when all the Fe plus 3 ion are, because as long as the Fe plus 3 ion are reducing, the current goes up. Now the concentration of Fe plus 3 ion is decreasing now. The current will decrease and a point will come where no current will flow, because again the concentration becomes equal for Fe plus 3 and Fe plus 2. So we'll get a peak current. Similarly here also we get a peak. After 4.176 seconds and at the voltage of 0.3521, the current is still going up. Again it is going to the top. This is the top and again it turns down. So it gives you a shape of a peak. So this shows that we have a peak current, and whenever you got either in LSV or in CV this sort of curve, this shows that you are not stirring the solution and you have diffusion as the mode of mass transfer only. the concentration of Fe plus 3 decreases while the Fe plus 2 concentration increases. The thickness of diffusion layer also increases and we get a peak current. As I told you that since convection is not taking place, only diffusion is there. So the thickness of the diffusion layer keeps on increasing, and from this equation we know that this current is inversely proportional to the thickness. As the thickness of the diffusion layer goes up, the current from its peak value goes down. Therefore, we are getting a peak because as the thickness increases, current decreases. They are inversely proportional to each other. Let us consider the concentration profile in an stirred solution. Again, see that this is the first curve where we have a system, electrode, we have ferric cyanide and a magnetic bar inside which is stirring this solution, or by some other means we are stirring the solution. Since we are stirring the solution, the concentration of Fe plus 3 remains uniform all the time. Even at one end near the electrode, the moment it gets it gets reduced to Fe plus 2, at the same time more Fe plus 3 ions will come, and due to the stirring of the solution, it becomes again uniform. And since this time we are having a uniform current, uniform concentration, the current also increases gradually. There is nothing like a peak current. There is no peak observed in this particular case. Initially, as in this case, we have first of all observed at point 0 smooth curve, no peaks. So again it is a smooth curve, while in this case we have a peak, we have sharp peak. Here we have quite a smooth curve. So this type of curve, even if it is a portion of a CV curve or a LSV, the curve will be smooth as long as you are stirring the solution. Most of the time we do not stir the solution in CV, so we get peaks. While in LSV we sometimes stir, so the curves are mostly smooth. Clear? Now let us talk of cyclic voltammetry. You all are aware in the previous few lectures on day 1, 2 and 3, especially on day 3, that cyclic voltammetry is a special class of voltammetry in which we scan the potential in both the direction, in forward as well as the reverse direction, and therefore we collect information of the forward process, which may be oxidation, and its reverse process, which is reduction, or maybe a forward process which is a reduction and its reverse process which is an oxidation process, because it is a cyclic process. I told you that in case of cyclic voltammetry, we select the potential window, for example, from 0 to 1, and then from 1 to 0, or from -1 to +1, and then from +1 to -1. So the potential varies in this manner. For example, we have select from negative, for example, -1, it is going to +1 and then back. Similarly, for example, if it is -1, it goes towards the positive side. Then from positive, it again goes to the negative side. So the potential varies in this manner. Draw this curve in your copies. This is the way potential is being monitored, or the potential is being varied in case of cyclic voltammetry. Now we monitor the current correspondingly, and then we plot a graph between current and voltage. The curve for the plot comes like this, called as a duck-shaped curve. These are the curves, and from this curve you can see that if I ask you, you find a peak over there. So in cyclic voltammetry, we vary the potential in two directions, and we study a detailed electrochemical process both in forward as well as the reverse direction. In this particular example which we are considering today, the reduction of Fe plus 3 to Fe plus 2 and then its reverse process. So first, if we give the scan, we scan the potential to a more positive value, for example -0.5 to plus 0.5, it shows oxidation of Fe plus 2 and Fe plus 3. So in the forward direction we have Fe plus 2 which is undergoing oxidation to form Fe plus 3. Then when this potential reverted, because if we are doing LSB only, it will provide information about this particular reaction, but not about this reaction. Since we are doing cyclic voltammetry, we will get information about the both the processes, both the reactions, the forward as well as the backward. So when the potential revert back from that predetermined value in the reverse direction, we'll get the reverse reaction, which is the reduction of Fe plus 3 to Fe plus 2. And we collect information and the potential and the peak current for both these reactions. Now the peak current in cyclic voltammetry is calculated by Randall-Savick equation. The peak current IP is given by 2.69 10 raised to the power 5 n to the power 3 by 2 a d 1 by 2 nu 1 by 2 and c. All these are constant except the word, this term C. C is the concentration of that electroactive species, the concentration of analyte for forward reaction. This analyte is Fe plus 2. For backward reaction, this analyte is Fe plus 3. ये रिएक्शन यहाँ से स्टार्ट होती है, ये कर्व बनना यहाँ से स्टार्ट होगा इस टाइप से, ठीक है. Now for forward reaction, you can apply the same equation. For backward reaction also you apply the same equation for forward, but for forward equation the concentration C is Fe for the concentration of Fe plus 2. For the other reaction it is for Fe plus 3. Now n is the number of electrons which are being involved. In this particular it is 1, because Fe plus 3 is undergoing reduction or Fe plus 2 is undergoing oxidation and 1 electron is transferring. D is the diffusion coefficient of the electroactive species. Nu is the scan rate. मैंने बताया था, you have to select the scan rate, at what scan rate you are changing the potential. And finally C is the concentration of electroactive species, A is the area, and from this you can calculate the peak current. Clear? So the CV curve starts from here and then it forms a duck shaped curve. So this is your forward process, this is your reverse process. This is your forward current, peak current, this is your reverse peak current. Clear? This is your forward peak current, this is your reverse peak current. Now when you calculate the peak current for both forward and backward processes, you divide it. And if the ratio of the peak current of the forward as well as the backward reaction is 1, the system is a well behaved electrochemical system. Means the total number of ions which are oxidizing is equal to the total number of ions which are reducing. For example, if 10 ions of Fe plus 3 are undergoing reduction to form Fe plus 2, same number of 10 ions are from Fe plus 2 undergoing oxidation to form Fe plus 3. Same number of ions are involved in the forward and backward processes. The same amount of current will be generated. The ratio of the peak current will be 1, and this shows you that your system is a well behaved system. On the other hand, if this value is not same, if this value is not 1, then that shows that there are some other reactions taking place. For example, if you have iron in plus 3 state, ferricyanide, it is getting reduced to Fe plus 2. Now the moment Fe plus 2 is formed, for example, if there is an impurity in the system which is very prone to attack on Fe plus 2, it will immediately attack, it will immediately react with Fe plus 2 to form a stable compound. Now since Fe plus 2 no longer exists, how will it form Fe plus 3? And if this is the case, the curve will be like this, that you get a peak in the forward reaction but no peak in the reverse reaction. Because in the forward reaction you have ions that undergo reduction or that undergo the electrochemical process to give you the other ion, but the moment it is formed, it is immediately reacted with some impurity as a competing reaction. It forms certain other compound. Now it is no longer left. Then who will revert back to via this reaction? So in this In the backward reaction, no peak will be observed. And in these two curves, you can see that we are getting peaks. That means we are not stirring the solution, convection is not taking place. For a cyclic voltammetry system, if you want to calculate half wave potential, just add the two peak current and divide by 2. So the half wave potential in a cyclic voltammogram curve is given by EPA, the peak anodic current plus the peak cathodic current divided by 2. So by dividing with 2 and adding these two current, you can easily determine the half wave potential for a CV system. Let us come to amperometry. Amperometry is very useful for sensing. Voltammetry is mainly preferred for energy storage applications. Even voltammetry can be used for sensing as well, but we prefer mostly voltammetry for energy storage and all those type of characterization and for sensors, because amperometry was very first developed for a sensor. It is the technique which measures current as a function of time at a fixed potential. The potential value is fixed. At that fixed value, we calculate current as a function of time. The technique, the amperometric sensor was first developed by, the first amperometric sensor was developed by L.C. Clark in the year 1956. And with that sensor, he measured dissolved oxygen in the blood. Now, what is the sensor all about? That sensor consists of? A sensor basically consists of two electrodes, and there is a membrane which allows only a particular type of gases to pass through it. He uses a gas permeable membrane which allows gases only to pass through it. That gas permeable membrane is stretched across a sensor in which the electrodes, there are two electrodes, then there is a KCl layer, and after KCl layer we have that gas permeable membrane. So at the top of the surface of the sensor we have gas permeable membrane, inner side we have KCl, and then we have electrode. I think I still have some time left. We'll be having tea at 11:30 or 11 o'clock. I think it's 11:30. Yeah? No, sorry, 11. Because today I started the lecture a bit early. Although it was scheduled on 9:30, I started at 9:45. So I'll continue it till 11:15. So the top layer of that sensor is a gas permeable membrane, then we have KCl layer, and finally we have two electrodes. One side we have this AG ring electrode, this ring is silver electrode, and at the center we have PT disc. Now that gas permeable membrane, when we put a drop of blood, it allows only gases like N2, O2 and CO2 to diffuse through it. N2 when diffuse, nothing will happen. It is not going to oxidize, neither CO2. Even when all three gases diffused inside, only oxygen will get oxidized. So nothing to worry that if N2 is also getting diffused, we should use only that membrane which allows oxygen only. No problem. If N2 and CO2 are there, only oxygen will get uh, reduced. Now when we put a drop of blood, the dissolved gases present passes through the membrane, reaches inside. The moment oxygen gets in, it is reduced, and iron, this oxygen gets reduced at platinum electrode, and iron electrode undergo oxidation. Ag forms Ag plus 2, Ag plus 1, and that electron is taken up by oxygen for reduction. In this way, electrons are moving, a current is generated, and this current is proportional to the concentration of oxygen. Higher the concentration of oxygen in the blood, higher will be the current, or vice versa. If you are getting higher current output, that means the dissolved oxygen concentration is high in the blood. So this was the first sensor, which is an amperometric sensor developed by Dr. L.C. Clark. Similarly, we have a blood glucose sensor, which we all are using, we all are aware of. A blood glucose sensor has an electrode where we put a drop of blood. Now, we replace the glass membrane, which is used in blood oxygen sensor, with three different membranes in case of blood glucose sensor. The first, the outermost membrane provides strength also. It provides as a, it is a protection also for the rest of the layers. This layer is made of polycarbonate, very strong. This polycarbonate layer is permeable to glucose and oxygen only. So when you put a drop of blood, first of all, this polycarbonate keeps the other layers protected, and when you put the drop of blood, only glucose and oxygen diffuse in through this layer. When it enters, because there are three layers, after this polycarbonate layer, we have a layer of an enzyme, glucose oxidase, which can oxidize glucose. The moment glucose and oxygen reaches there, the glucose is oxidized by glucose oxidase immobilized enzyme, immobilize कर देते हैं, layer बना देते हैं, to form gluconolactone. Electrons are released. On the other hand, the third layer is cellulose acetate. Immediately the oxygen is reduced and it forms H2O2. The polycarbonate membrane allows glucose and oxygen to pass through it, where glucose is oxidized to gluconolactone and H2O2. Now H2O2 is oxidized to oxygen, and in this way, H2O2 is oxidized to oxygen, and in this way, a current is generated. And since the electrons are being released from glucose during the formation of gluconolactone, these electrons are proportional to glucose concentration. So the current is proportional to glucose concentration. If the amount of glucose in blood is high, the current will be high. So this is also an electrochemical sensor, or electrochemical sensors gives you either value in the form of current or the voltage, and this current and voltage is directly proportional to the amount of or the concentration of analyte. And in this way, based on the value of the current generated, there is already a calibration curve drawn and fitted well into the transducer. The transducer is the machine that converts that data into useful information. So on the basis of that calibration curve, from the current value, it calibrates backward to give you the concentration, to give you the amount of blood, to give you the amount of glucose in your blood. Now, what points one should consider while selecting an appropriate voltammetric technique? Amperometry, we have this technique only. In voltammetry, there are several techniques. These are the techniques which I have shown during the classification. These are different techniques: hydrodynamic, stripping voltammetry, then we have LSV, we have pulsed potential voltammetry, then we have CV. So which technique we should use for our analysis? So there are certain points which must be considered. The choice of voltammetry depends upon the nature as well as the concentration of sample and its location. For example, you are doing analysis of something in a flow system. For example, you are analyzing some component in blood. So it is a type of flow system. We always prefer amperometry for that, because amperometric sensors are portable, they are more reliable, and they can be used for real-time analysis. Now, if you have to use voltammetry techniques, then we have to first of all know the possible the concentration limits of the component. For example, if we are using polarography, the limit of detection of polarography, if we compare it with stripping voltammetry, is less. Stripping voltammetry means we are using a voltammetric technique in which we are stirring the solution, in which we are allowing convection to occur as a mode of mass transfer along with diffusion. The stripping voltammetry may we allow the convection to occur along with diffusion. So if we compare the limit of detection of stripping voltammetry is much higher. Means if we can detect even very low concentration, 10 to the power minus 12 molar. So if some analyte is present at very low concentration, for example 10 to the power minus 11 molar, and if you detect it with polarography, you won't get any answer. It shows that the analyte is absent. But if you use the stripping voltammetry, it will give you a reliable information about the concentration of that analyte. So we have to select a particular technique depending upon the nature of sample, the nature of media in which we are. For example, it may be flowing water, it may be blood, or whatever it is, and also on the limit of detection as well as sensitivity of the technique. Thank you very much for patience listening. I think I have taken 10 or 15 minutes extra. If you have any question, I would be happy to answer. Anyone from the online participants also? Fuel cell, I can explain, but it will again take more time. One more lecture is needed for fuel cell. But in fuel cells also, we characterize a fuel cell as well with the help of cyclic voltammetry, because in fuel cell also, fuel cells are basically energy generation devices. Or you can say energy converting device. They convert, for example, a fuel cell either convert a chemical energy into electrical energy, while batteries and capacitors are energy storage devices. So both involves energy either in the form of storage or in the form of conversion. So we characterize a fuel cell also with the help of CV and LSV. Let's move for a cup of tea and then we'll back again in this room. Thank you, sir. Thank you. If we are selecting a very high scan rate means the potential is varying at a very high speed. It will allow lesser time for the electroactive species to respond. Sometimes due to very high scan rate, there may be the oxidation and reduction process missing. If you allow, if you selected a low scan rate, you are allowing sufficient time for electroactive species to reduce or oxidize. So it is always preferred not to take very high scan rates. Any other question? Voltamammogram, that I'll explain you when we have a machine. Tomorrow, if possible, we'll try to bring the machine as well. Then I'll explain you how we can. That I was the same question. The scan rate, if we are taking very high scan rate, the system's potential is changing at very high speed. For example, you have certain reaction occurring at 0.4 volts and you are changing the potential at very fast pace. So it will not give sufficient time for the species to undergo oxidation and reduction. The chances that either it will not observe or observe to a very limited degree. So you have to give sufficient time to the electroactive species to respond. That's why we do not generally select very high scan rates. Anyone from? So let's move for a cup of tea, then we'll come back again. Thank you.
for the most awaited lecture of this today's program. We have with us a Dr. Shahab Ali Asghar Nami, the chairman of our Industrial Chemistry Department and co-organizer of this GIAN program. And he is a distinguished speaker and academician, and his research interest thrust area is basically the nanomaterials and applications in the wearable electronics. Dr. Nami earned his PhD from Aligarh University, and there has been associated very different prestigious institutes like IIT Kanpur, IIT Bangalore, and other institutes in Korea as a postdoctoral fellow. And he is also a recipient of Indo-Hungarian exchange program visiting faculty program. Now I request Dr. Shabri Zanana, please come and give an insightful lecture on nanomaterials and their variable technologies and electronics. A huge round of applause for this.
Thank you, Dr. Muhammad Asfar Shada, for the nice and scintillating introduction. So, Dr. Muhammad Zain Khan, course coordinator of this GIAN program, esteemed colleagues, and my always dear student. Assalamu alaikum and a good morning, and welcome you to this fourth day, second session GIAN program. So today we are going to, dive into the multifunctional hydrogel chemistry. And this chemistry is exciting, and I'm also excited to share with you the benchmark chemistry, which is actually originating on the interface of chemistry and technology. So multifunctional hydrogels will be covered in this lecture, and we will see the applications in soft robotics and wearable electronics. So let us quickly go through this overview. Okay, so this is the overview of the contents which we are going to explore today. Initially, we are going to study the multifunctional hydrogels, and all of us know that hydrogels are a class of compounds that can absorb tremendous amount of water. Ideally speaking, an hydrogel can absorb around 30% or 30 times more water as compared to its dry state, which is called as a zero gel. So this amount of absorption of high amount of water actually relates somewhere chemically to the functional aspects of hydrogel. Chemically, hydrogel can absorb water only if it can form perfect hydrogen bonds. And for forming a perfect hydrogen bond, the hydrogel must contain certain hydrophilic functional groups, notably the amine group, the amide group, the carboxylic group, the you can say hydroxyl group particularly, and so on and so forth. So we are going to study a little bit of our own findings, and then we are going to study these fascinating hydrogels with regard to their incorporation of nanoparticles. And there has a lot of talk about nanoparticles and graphene oxide, and today we are going to see from the arena of hydrogel that how the incorporation of these beautiful nanoparticles having intriguing properties, and how these graphene oxide, which is talk of the town today for the previous 3 days, that how the incorporation actually changes the properties of these hydrogels, both in terms of conductivity, in terms of tensile strength, in terms of their optical properties. So we are going to explore that also. With regard to the wearable electronics is something which is very close to my heart. And in fact, when we go through those wearable electronics, then you can see that all the Hollywood films which you have seen are going to come true. Okay, so then we are going to study it in terms of artificial muscles, that how these hydrogels can be modulated and how these are going to are replacing These are these muscles, the human muscles. That is how these hydrogels are, gaining importance. What is actually the properties which are making it so robust in terms of replacing various human organs, be it the lungs, be it the skin. So we are going to study that also. Then after all, every good thing has some bad things also. So we are, going to witness certain challenges also. That what are the challenges? What are the aspects which are need to be fit in? And at that point of time, I'm going to urge my young minds to find solution for these challenges. And then we will see the future directions, that what else can be done. And definitely, as I have told you, that these hydrogels are making mark in every field, be it material sciences, be it biomedicine, be it targeted delivery, be it tissue engineering. You can just name the field, I will name you the application of hydrogel. That's for sure. So then we see the bio-inspired design. We will see the beauty of nature. We will together adore that how nature is always on the forefront and the human research is on the back front, if you think in terms of nature. We can see that how a plant, a carnivorous plant is mimicking, and what is the speed of tackling its prey, and how the hydrogel is coming into play with that hand in hand. So we will see in that slide. Now, as all of you are aware, and most of you are still using IoT, that is the Internet of Things. So we will be going to see how this marriage is going to happen between the hydrogels and the Internet of Things. So then we will be studying the smart actuators, and we will see that how these comes on into play. So let us begin our journey. Let us embark on the journey of hydrogels. I have to put my glasses. Okay, so hydrogels. As I've told you that hydrogels are three-dimensional polymeric materials which are entangled by physical cross-linking as well as chemical cross-linking, which we will going to study in the coming slides and more details. So these hydrogels are fascinating materials having extra toughness, having extra conductivity, having extra sensing. That is, you can say that hydrogel are the next class of the wearable skin. Why I am saying skin? Because the hydrogel have the propensity to feel. They can feel. They can self-heal, just like the normal skin. They can self-heal. Very recently, maybe 3 or 4 days back, there was a research that a group of scientists have prepared a hydrogel which can heal the skin around 75% in just 6 hours. So you can see, you can visualize that how this hydrogel can be becoming vital in our future. So these hydrogels may be regarded as heroes. And the moment you talk and you incorporate nanoparticles into them, they become superheroes. So why I am saying superheroes? Because you all know for the past 3 days you are listening a lot about nanoparticles. Nanoparticles, as I have told you in my inaugural address, that the moment you go from bulk to nano level, the property changes. And the good thing or the bad thing about nanoparticle is that you cannot predict. You cannot predict. For seeing a material in bulk state, you cannot predict that how it's going to behave in terms of conductivity, in terms of tensile strength, in terms of optical properties. You cannot predict that how it is going to behave when it goes into the nano level. And that makes this class intriguing in nature. That is, this makes this nanoparticle a research area which is open to all, not only to chemists. This is a research area for biochemists. This is a research area for biotechnologists. This is a research area for medical scientists. Because you cannot predict. If you want to have an idea, you have to, do a research in it. And for each nanoparticle, you need to do a separate research because you cannot predict. There is no hard and fast rule where you can predict the properties of nanoparticles. So my hero becomes a superhero when it adds the nanoparticle in it. That is, when you incorporate nanoparticles, be it the ceramic based, be it the metal based, be it the polymer based, any type of nanomaterial, if you are going to incorporate, then definitely there is a synergic interaction. And we are going to witness, we are going to explore that synergism between the nanoparticle and the hydrogel today. So, on my slide, if you see, there are certain recent developments where a graphene is incorporated in a hydrogel, and that actually leads to the development of high performance sensors. Similarly, when you incorporate silver nanoparticles into a hydrogel matrix, then definitely you will find that it shows or it becomes wearable strain sensor. At the same time, on a biological scale, it becomes a very good antibacterial agent. But again, there is a caution point. There is a caution. If you are going to incorporate any nanomaterial, then you have to make sure about the quantity. Then you have to make sure about the structure of the nanomaterial, because chemistry becomes history without a structure. So you have to make pretty sure that what type of nanoparticle, what is the shape of the nanoparticle, what is the nanodimension, what is the properties, because as far as the constructive interference is observed, destructive interference is also there. So you have to have a synergic interaction between a nanoparticle and a hydrogel. So today we are going to explore the synergism between a nanoparticle and a hydrogel. So it's an overview of multifunctional hydrogel. Now, hydrogel we all know. Why we are using the word multifunctional? Why multifunctional? Multi, of course, means many. Now, why this many? Many comes from the extra conductivity. Many comes from the responsiveness. Many comes from the optical properties. And all the properties which I am saying are enhanced in a constructive manner. And the stimuli response, that is actually, that is the most beautiful aspect of hydrogel. That is the stimuli response. That is, these hydrogel responds to a change in pH. These hydrogels respond to a change in pressure. These hydrogels respond to a change in temperature. These hydrogels respond to a change in concentration. And that makes them the best one with regard to their application as a targeted drug delivery. Because, the human body is the marvelous creation of the God, or you can say the nature. Because it is the only place where acid and base exist or coexist. The moment a food enters into the esophagus, it goes from acidic medium, then a little neutral, and then to basic. You cannot find any place on earth where acid and base are meeting and still they are separated. The pH in the stomach is so strong that if you just put a nail in it, then the nail will dissolve. Similarly, a basicity is also there around pH 12. And pH, all of us know, is pH stands for yes. Any other brilliant answer besides this answer? No, I'm more interested in knowing that what P stands for and what H stands for. Very nice. But the more authentic word for P stands for puissance, and H stands for dehydrogen. It's a French word actually. If you do not Google everything. Google is not always right. So do not believe in a blindfolded manner on Google. If you search in some good foreign author book, then you will find pH stands for puissance dehydrogen. Of course, what you are saying is right. That is negative logarithm of hydrogen ion concentration. Of course, I appreciate and I fully agree, but pH stands for puissance dehydrogen. So, coming back to our thing, that these, that is, the stimuli responsiveness make them hydrogen apart from all the class of soft gel things. Okay? So, one of the recent advancement, as I have told you earlier, is the incorporation of carbon nanotubes. We know that these carbon nanotubes have exceptional conductivity. And if we are going to incorporate them in the hydrogels, then these hydrogels also become superconducting. Similarly, with regard to muscle tissue, if you are going to add a little bit of silica, silica bridges, then they give exceptional tensile strength. And they become valid, they become vital for the replacement of muscle tissue. So, we are going to explore this a little more in detail. Now, the properties. As I told you earlier, that the multi means the spatial aspects. The spatial aspects arises because of the extra elasticity. That is, these hydrogels are elastic, and at the same time, if you stretch a little bit more, and if there is a crack, then they can self-heal also. Just like your normal skin. If you get a cut, then after a certain period of time, this healing starts. And the hydrogels are doing the same. And that is why they are the best alternative for artificial skin. So, what I am going to say is that these are the properties which are replacing all these things. That replacing your age-old conductors, replacing your age-old turmeric creams, replacing your age-old, the age-old things, and they are actually entering in the each and every arena of human beings. So, with regard to, electrical conductivity, there's a lot of talking about graphene, and I'm also very much interested in graphene, which I'm going to show you my research, a little bit of research on graphene, that graphene has exceptional stability, has exceptional strength because of its structure. And how we are going to capitalize this in hydrogels, we are going to see in the coming slides. So, I've already told you about the stimuli response, that how these hydrogels respond to the external stress. Now, instead of stimuli, I am saying the word stress, because for a hydrogel, it is a stress if you are going to change the pH medium. It is a stress if you are going to change the, the light mechanism, because that hydrogel has to adjust itself. Otherwise, if it is not responding, it is not responsive. And if it is not responsive, it is of no use to us. Okay? So, now the significance of, our superheroes, that is nanoparticles. Now, as we have already discussed, the nanoparticles are, are ubiquitous. That is, they are everywhere. They are everywhere. And if you remember, we are using nanoparticles before the Europeans. We are using the nanoparticles before the Europeans. Why I am saying this? Because if you remember the suit, if you remember that the kajal, that was actually a formulation of nanoparticles. But because of the lack of research, because of the lack of instrumentation, we do not know that we are using the nanoparticle from our, from our generations. So that is the nanoparticle. Now the nanoparticles are bestowed up with special, strength, with the special conductivity, with variety of functionality. And day before yesterday, we have seen that how actually you have functionalized the graphene, how actually you have used the very strong mineral acids, and how you functionalized it. And we are using that functionality in our research. So, type of a nanoparticle. It is just a routine slide, because I suppose now you are the masters of nanoparticles. But I have to reiterate again that we have carbon-based nanoparticles, we have metal-based nanoparticles. And the moment I say metal-based, the first thing which comes to our mind is our very familiar silver nanoparticle. Similarly, we have gold nanoparticle. Now, gold is making sound more than silver because of the low toxicity, and at the same time because of the high efficacy. Now, gold nanoparticles are being used as anti-arthritic drugs. And the best anti-arthritic drug is the combination of gold nanoparticle with the betel leaf. All of you know betel leaf? That is the palm. Yes, anything which is in a in a very defined state is good. So chewing of betel leaf is good, but not to a large extent. So betel leaves along with gold nanoparticles is one of the best arthritic drug which has recently been known. So with regard to polymeric nanoparticle, their beauty is the biodegradability and the biocompatibility. Now these two words always go hand in hand, that is the biocompatibility and biodegradability. Most of the time we actually bank on biodegradation, because if we are using our system in a human, then we have to ensure that that must be cleaned. The human system must be cleaned. That is, we are using hydrogel as a vehicle, so vehicle must go out from the body so that it cannot create any further toxicity, because we are using these hydrogel as a drug delivery agent, or you can say the targeted drug delivery agents. Similarly, the ceramic based nanoparticles, they are very exceptional in terms of their strength. They always provide extra strength, and as I told you earlier, that a recent research has shown that if you tag the hydrogels with the silica based nanoparticles, then you are getting a very good skin which has a healing of more than 75% in just 6 hours. So you can understand the robustness of these self-responsive hydrogels. Okay, now coming to a little bit of chemistry, that is, what are the different ways by which we can synthesize? Of course, we can synthesize by them by in situ polymerization. Now, in situ polymerization means that everything in one place, that you have to add everything in just a one vessel, one by one. Now, this 1 by 1 and 1 by 2 and 3 is very important. That is very important. That is, if you are using, for example, if you are synthesizing system made up of 4 components, A, B, C and D, then this hierarchy is very important. That is, what you have to add first, what you have to add second, and what you have to add last. Now, what is the rule? The magic rule is you have to look for the functional groups, because chemically speaking, no reaction is 100%, and chemically speaking, no reaction is 0%. All the reactions range from 0 to 100%, and the reaction which we generally depict by A plus B is giving you C is the main reaction. But besides the main reaction, certain competing reactions are also going on. Certain parallel reactions are also going on. This we have already, we have already discussed. If my students remember, this we have already discussed during the study of our catalysis. So these reactions go hand in hand, and the best one, that is the rule of the universe, survival for the fittest. So the best one, the most stable one will be the major product always, but you cannot ignore the minor product. So you have to work, you have to prioritize your A, B, C and D depending on the functionalities, of polymers. For example, if your component A and component B are rigid in, for example, aniline in amine group, for example, then you cannot treat them. Then you have to think for a component which has dominant carbonyl group. Only then you can have a good reaction. A good shift-based reaction is there. Otherwise you cannot. So you have to establish the hierarchy in terms of their structure, in terms of their functional group. So that is the beauty of in situ polymerization. And the good thing with in situ polymerization is that you have always very good yields, because in terms of in situ, you are adding everything in one vessel. So there is always chances of very high reactivity and very low inactivity. Similarly, you have the blending. That is, you just take one component, another component, or maybe third component, and you just simply mix them and then you blend them. That is a simple one, but not very effective one. Similarly, you have surface modification. Here comes the chemist. Here comes the traditional chemist when you say surface modification, because you have to modify your surface with regard to the functionalities of your components. Sometime you have to have the carbonyl groups as a dominant group. Sometime you have to have amino group as a dominant group. Sometime you have to have amide group as a dominant group, so that you can have an effective good reaction. So each of this method has its certain advantages and each has certain disadvantages, and you have to work on this while working on the table. So cross-linking mechanism. Now comes some intrinsic property of hydrogels. As we know that hydrogels can be of two types broadly, that is the physically cross-linked hydrogels and the chemically cross-linked hydrogels. And these are classified on the basis of the type of bonding present. For example, physically cross-linked hydrogels are those which contains physical cross-links, physical bonds, that is the hydrophilic hydrophobic interactions, the hydrogen bonds, the weak van der Waals forces. Similarly, as far as the chemical cross-linking is concerned, we have simple covalent bonds between the components. Now again, there is an issue. There is an issue with regard to cross-linking. Cross-linking is good, but high cross-linking is not good. Because the moment you increase the cross-linking, its property of absorbing a fluid decreases, because you have squeezed the space. So you have to have an equilibrium. You have to have an equilibrium between the cross-linking and its ability to absorb a fluid, generally water. So in case if you increase the cross-linking, then you are squeezing the space so that there is less space for its ability to hold that particular fluid or water. But at the same time, if your cross-links are not strong, then there are chances then that your hydrogel may degrade. It may lose its physical state. So you have to have an optimum equilibrium between cross-linking and the ability to absorb or hold fluid. Now characterization technique. This is very much vital. Vital in the sense that if you have prepared a loin in the lab and the instruments is telling that it is not roaring, it is barking, then definitely you call it a dog. This is like this. So you have to have full establishment with regard that what you have proposed is absolutely prepared, is absolutely being synthesized. And for this, you use a variety of spectroscopic techniques. You use a variety of morphological techniques. And for ascertaining its stability, you use a certain thermal techniques. With regard to the structural determination, with regard to the functionality, you have to use our age-old technique that is called as the IR. Now what is the basic principle of IR? Yes, my dear students? What is the basic principle of IR? Yes, I urge my students, it's still a day. Yes? A little loud. I'm not good at hearing. I'm only good at talking. So the basic principle of IR is the change in dipole moment. Change in dipole moment. And what is the basic principle of Raman which we are going to study today? Change in polarizability. So we are using FTIR just to confirm the functional groups, that what are the functional groups which are used and what are the functional groups which are still left behind, so that we can add on our monomer. So we are using FTIR, we are using, in terms of morphology, we are using SEM, we are using TEM, scanning electron microscopy, tunneling electron microscopy. One is based on the back radiation, one is based on the incident radiation. Similarly, we are using XRD, which uses the HKL planes. Similarly, we are using, in terms of, we do not have good techniques, but AFM is also very good. And Professor Hitao was saying 3 different types of, he has shown in his slide 3 different types of AFM. And I was wondering that I only know 2, not the third one. So this is actually what is, what is the lack of instrumentation we have. Anyways, what we have to cherish on it. So we are using SEM and TEM for morphological characterization. Similarly, with regard to conducting studies, we'll be using different instruments like conductivity bridge, etc. Now this is a synthesis reported from our lab. You can see the graphene oxide, simple graphene oxide charged with carboxylic groups. And what is the beauty of this? That we have reported our in situ synthesis or in situ polymerization. We have used graphene oxide and we have used chitosan to have some biocompatibility, to have some biodegradability. And then we use our best conductor, that is the cheap conductor, that is pyrrole monomer. And we have actually have an in situ polymerization of this. And we have successfully synthesized, you can say, a nanocomposite. And these are the images of the SEM. Now, on your left, you can see the wrinkled graphene oxide, the characteristic perfect wrinkled graphene oxide. Now, the moment you form a ternary complex, can you wake him up? Okay, so the moment you convert into ternary graphene, to a ternary nanocomposite, you can see the structural difference. And the TEM is, the TEM is a witness to it. You can see that how the wrinkled structure gets lost and you get pieces. This is, you can see the beauty of these ternary nanocomposite. And practically what we have done, you can see the dye removal efficiency of this. This is the study reported from our lab. You can see a clear-cut difference with regard to the concentration, increasing concentration in ppm. And we have removed the Congo red dye. And this study was reported in Polymer Composite Journal, a good journal with regard to material sciences. Now, from this good results, we put a front forward, and then we have utilized a fully ternary hydrogel. Now these ternary hydrogels are actually fully biocompatible. Biocompatible in the sense that now we have all the three monomers are compatible, biodegradable, and now you can see that we have used CMC, we have used glutamic acid, and we have used chitosan. Glutamic acid you will be taking in your lunch today, because no food can be cooked without glutamic acid. That is your beautiful garlic. Garlic contains glutamic acid. So we have used glutamic acid, and we have used glutamic acid as a cross-linker. Although in the diagram you can see it as a monomer, as a component, but it actually is a linker. It is a linker. And you can see that on one hand we have an ester linkage, and on the other hand we have an amide linkage. And they are actually prepared in a very good yield. And again, you can see the removal efficiency. Now we have used two dyes. On the upper side you have methyl orange. On the lower side you have amido black dye. And the beauty of the dye removal is that it is working in both the conditions, that in the acidic media and the basic media. That is the robustness of this ternary hydrogel, that it is equally good for the removal of cationic as well as anionic dye. So we have published our finding recently in last year, and this actually this is actually work of my MSc students. So now the heart of our the talk, the wearable electronics. Now, as the word is saying itself, wearable electronics, and wearable, that we can wear, that you can regard hydrogel as a fabric of future, that in future you will be wearing a shirt of hydrogel, maybe. Because now it's high time that you are using these hydrogel as in the form of patches to monitor your glucose level, to monitor your hypertensive effect. You are using these to, to know that whether you are happy or not. Because it has the ability to change color depending upon your response of the body, because they are all responsive. And that is the beauty of these hydrogel, that is they are highly responsive. They are just like the human skin. Where, and all of us know that what is the difference between a good touch and a bad touch, and hydrogel can tell you that. So you can understand the robustness of this, that it can sense. And in the coming slide we can see its speed, its robustness. Okay, the applications of hydrogel. As I have told you that they have numerous applications. They have applications in health monitoring. Just now I told you that we can have in the future patches to determine our emotions. Our emotions can be reflected by the color of hydrogel. Okay, if we are wearing hydrogel and your hydrogel is green and mine is red, then you are not going to talk with me because I am red. But if you are green and I am green, then okay, we will talk. This is like this. In the future, this is going to happen. It's not a Hollywood movie anymore. We are going to talk on the basis of the patches. So I urge you to take this opportunity, that the future of hydrogel is very bright and there's a long way to go. So at the same time, they are flexible. They are flexible and they can be used in semi-arid as well as humid conditions, because now we are able to prepare hydrogels. And if you remember the first slide, this is my hand and this is the hydrogel which we have prepared in our lab. This was prepared late back in winter. So we have prepared a hydrogel which is very good adhesion property, and still we are working on it. And for research ethics, keeping in mind the research ethics, I am unable to tell you what are the components, but still we are getting very good, marvelous results. So now we have to, the hydrogel is in our lab is ready. And the only thing is we have to ascertain that whether it is responding or not. So we have achieved two things. We have achieved the good adhesion and we have achieved a good tensile strength and a good workability. But application part is in progress. So coming back to our slide. So they are flexible, and recently you have heard that in Bangalore now the robotic mates are there. Now for a robot to become a maid, she must have a mother's touch. She must be sensible. So all these properties are to be incorporated by using the hydrogels. And how they are being incorporated, we will be seeing in the coming slides. So the role in energy harvesting. That is actually the area of Dr. Mohammad Zain Khan. I am not going to encroach much in that energy harvesting. But still, these hydrogels are very good in terms of energy harvesting, because we can have piezoelectric hydrogels where we can convert mechanical energy into electrical signal. And that is actually one of the major application where we are going to use the hydrogels. Similarly, triboelectric nanogenerator. That is one of the very recent area. That is very fascinating. Fascinating in the sense that if you are moving your fingers, then you are actually making some physical movements, and by making some physical movements, you are generating electricity. You are generating electricity. You are generating power, and you can use this power to further do some other works. So just by the movements of your hands, movement of your body, you are going to generate electricity. And that is only possible by using triboelectric nano generators. And that can also be incorporated in the hydrogel. So you can understand the beauty, the robustness, the versatility of these hydrogels. Okay, now comes our nature. Soft robotics. Most of the soft robotics are actually bio-inspired. They are biomimetic. They are biomimetic. Biomimetic in the sense that, for example, you can see a jellyfish or you can see a starfish. Its movement is so smooth then that it catches the prey and the prey does not know that starfish is very close. And we have prepared a hydrogel, and that report was published in Science Robotics 2023, where they have prepared a hydrogel which can move so swiftly that its movement cannot be recorded. So now the artificial muscles. Hydrogels mimic the muscles and they have very precise movement. You have heard the robotic arm. You have heard the robotic arm surgery. Soon you will be going to heard about the hydrogel based surgery. Similarly, soft grippers. Now, because these hydrogels can sense, these hydrogels can self-repair, these hydrogels are responsive, so they can also have the mother's touch. Earlier what happens that the traditional robots, when they try to hold the things, they have a very strong grip. Now, if you ask a robot, a traditional robot, to bring some eggs, then okay, it will going to grab 3 eggs, out of which only 1 will be in the proper state, other will be cracked. But by using the hydrogel, you have a soft touch. You have a soft touch, a smooth touch, a touch which is responsive. It can respond and it can adjust with the external stimuli, with the environment. So this is like this. Now how the nanoparticles comes into this arena? Nanoparticle actually enhances most of the properties. For example, in terms of conductivities, nanoparticles enhances the conductivity. For example, if you are going to incorporate multi-walled carbon nanotubes, then of course they have a very high conductivity. Now for say, if you are going to reinforce silicon, SiO2, then by reinforcing SiO2 bridge, you can have a better stability, better durability. Similarly, if you are going to install certain ceramic material, then you have very high tensile strength. In one of the studies, they have incorporated silver nanoparticles in the hydrogels, and these hydrogels can be effectively used as ECG patches. So these, if you remember, if you are keeping a close eye on my slides, then you will see all the references only 1 or 2 or 3 years old. Did you notice that or not? I was shown all the references after 2020. That is, most of the references are after the COVID era. After the COVID era. So you can understand that how much faster pace is involved in terms of research in this burgeoning area of hydrogel research. Similarly, now there are challenges. Now you can see the other face of the coin. Other face of the coin, that is, there are certain aspects which are to be addressed. And number one aspect with regard to the nanoparticle incorporation is the uniformity, the uniform dispersion of nanoparticles. So we have to think in terms of chemistry. We have to think in terms of devising methodologies where we can incorporate nanoparticles in a very uniform manner. We have to avoid agglomeration. We have to avoid stacking. Because what happens is that if your nanomaterial, for example, graphene, Graphene generally give rise to stacking. Stacking happens, and the moment stacking happens, the same hydrogel shows different properties. Because all the properties are dependent on the structure. The moment you change the structure, the properties will change automatically. This is something for sure. So you have to address this issue, that you have to have uniform dispersion of nanoparticle. You have to avoid aggregation, you have to avoid agglomeration, you have to avoid stacking. Now stacking is like this. This is stacking. Stacking is generally done in case of planar structures. Planar structures always stack one after other, like this. While particles agglomerate. Scalability is another issue. Because most of the nanoparticles are too expensive to incorporate. Although we have some silver lining is there in terms of scalability. If you are going to synthesize your nanoparticle by using biogenic approach, then of course you can avoid harmful chemical. Of course you can avoid high cost. Only if you are using the biogenic approach. But not always. Similarly, I have already told you about the cost. So you have to have certain alternatives of these costly nanomaterials. Okay, now comes the real problem with regard to toxicity and biocompatibility. Toxicity is something very inherent. For example, calcium is an essential element for us, but after a certain limit, it becomes harmful. It occurs in the body in the form of cataract. Similarly, copper is also an essential element, but a little more can cause a Wilson disease. So you have to make sure that the element, that the metal or any substance which you are using must be in the permissible limit. So similarly, there was a study reported in toxicology reports in 2023. Again, you are seeing the year of my reference. It is 2023. It is not the reference of my father's time. It is the reference of my time and your time. Okay. So you can see that silver nanoparticles, an excess can reduce the cell viability. Similarly, biocompatibility is also an issue, because you are using this hydrogel straight on the skin. So you cannot compromise it. You cannot use harmful chemical. So you have to find alternative ways to have compatible hydrogels. Degradable for environmental concern and compatible for human. So you have to have biocompatible and biodegradable. Okay. Environmental impact. So natural polymer based hydrogels. Definitely we have to use only those hydrogels which are degradable. Otherwise, what you can do, what will be done, that you do a work for 1 rupee and you create a problem for 2 rupee. So you have to avoid such type of materials which are not biodegradable. And that is why most of the time we are using cellulose based hydrogen. And as far as cellulose is concerned, I remember a study which we reported from our lab, and unfortunately it was not published. We have prepared a nanocellulose based eardrop in our lab. And because we were unable to find some good collaborator for testing it on human system, that nanocellulose based hydrogel was actually ointment based, where the hydrogel was sustainable deliver of that particular. For example, we have used it for dextran 6. So it was releasing that chemical in a sustained manner. So instead of using eye drop 3 times a day, you just put a hydrogel once in a while, and okay, Now from morning to night, no need to put no need to put drops again and again, because that hydrogel is going to release the drug in a very sustained manner for 12 hours. So that was our research. Unfortunately, it was not published, but we look forward in doing more and then publishing it in some good journal. So cellulose by hydrogel with embedded nanoparticles can be degraded within weeks. And this was a study published in Green Chemistry, again, the year 2023. Similarly, we should have a sustainable synthesis. And sustainability is one of the major goals of Government of India, that is SDG 3. Sustainable Development Goal, SDG. And if you remember the G20 summit, that is one of the goal. SDG was one of the goal. Okay, now the future. Now the research is in your arena, is in your area now. Now what can be done? So we can prepare hybrid nanocomposites by combining different sort of nanoparticle, because this type of studies are still very rare, where we are using more than one type of nanoparticle. In most of the studies you have, if you go through those studies, in most of the time we are only using silver nanoparticle throughout. We are using gold nanoparticle throughout. We are using platinum nanoparticle throughout. We are using tin nanoparticle throughout. For example, for anti-fouling agents, we are using tin nanoparticles for making the anti-fouling paints. Nowadays we are using tin nanoparticles because of the strong antibacterial action. But we are not using, we are not using a combination of nanoparticles. Now think in that direction, that if we are using a combination, then can we use them in a synergistic manner or not? So this can be a problem for your research also. Similarly, if you are going to have carbon nanotube and silica nanoparticle, then it can be shown that they have improved the mechanical strength as well as the electrical properties. For example, CNTs enhances the electrical property, while the silica has improved the mechanical strength. So similarly, we can think of using different nanoparticles in a single platform. Similarly, we have bio-inspired design. That is a topic which we will be discussing. Yes. Okay. Bio-inspired designs. Bio-inspired designs are very important. Let me tell you a very basic, aspect of bio-inspired design. Japan was the first country who developed tube trains. And initially, the tube train that was developed was like the conventional train, that is having the face like front face in a flat manner. And when these trains were tested at a speed of 200 km, what was observed was that when this train passed through the tunnels, then there was such a noise flux that the adjoining areas, that the people living in adjoining areas found that their window panes and the doors were broken because of the extra noise flux. And the government of Japan then deputed an engineer to look into it, to modify the design. And these trains in Japan are called as Shinkansen. These trains are called as Shinkansen. And my students can be seen smiling because they know it, what I am going to say. So that engineer actually look different and draw different models. And once he was sitting in a park where a river was flowing, he saw a kingfisher. Kingfisher, we all know kingfisher. And kingfisher is actually going for a prey, and he was observing a fish which is in the water. And what kingfisher done to catch its prey, it quickly draw its beak into the water and catches the fish. And what that engineers observed is that once the beak was inside and the fish was caught and the beak come outside, there was no ripples. There was no ripples. That is, there was no production of sound waves in the water. There was no ripples. And there he got the design. And then he designed the train in a beak manner. You can always see tube trains in a beak manner to avoid the noise flux. So this is bioinspiration. This is the biomimetic property. This is the power of nature. That nature has already designed everything. Now it's our task to look into the nature and get motivated and keep the things in right direction. So bio-inspired design. I will be talking about one more design in the coming slide. So we have to have our hydrogel in a biomimetic manner. Similarly, nothing can be left or nothing can be done in infancy without using the artificial intelligence nowadays. So we have to optimize our nanoparticle and the hydrogel based formulations in an AI designed manner so that we can have a 24/7 you can say monitoring of our hydrogels, in particular in terms of healthcare. Okay, so bio-inspired design. Now, another example is the Venus flytrap. Venus flytrap is actually a plant. And this plant is actually native to Africa, but its discovery was done in North Carolina, USA. What happens is, it is a cactus-like plant and it keeps its mouth open. And whenever some fly, anything comes close to it, it catches from its jaw. It closes jaw. And it closes its jaw in such a speed that you cannot even blink. That is the only plant nowadays established which is carnivorous, because its main prey is the spiders, not the air flies. So hydrogels were designed on the basis of that, and that finding was published in Soft Matter in the year 2023. That is, you can see that hydrogels can be designed in such a robust manner. And of course, human skin, which is nowadays is the largest organ of our body, we can design artificial skin by using hydrogels. And the beauty is that hydrogel based skin repair itself like the normal skin. And the repair is faster than the normal skin, than our original skin. So that is making actually a lot of difference in medical health care, in burn cases, in accidental injuries. Okay, now we have to integrate our things with the internet. So what actually, we are also working in this area, and recently I have been awarded one project from UPCST to work in this arena. So what we are thinking of making a patch and putting some material into it that can sense the sugar level. Dr. Zain Khan has also delineated about that how that cell actually works. But we are thinking in terms of hydrogel, that how we are going to induce it in the hydrogel, and this incorporation is actually very friendly to the person concerned or to the patient. Now, by developing such patches, we can remotely access the patient's state, because we can monitor it on our mobile phone, we can monitor it on our laptop. So this study has, a little bit of a study has already been published in IEEE journal, and now we are also exploring to develop this on an indigenous level. Although this type of patches are known with limited facilities in Europe. Okay, so development of smart actuators. So what we are going to do is we are going to study it under different electric fields, and already this has been reported with regard to the robotic arms. And again, you can see the study, it is still 2023. So all these are very, the development is very rapid in the area of hydrogels. Now, coming to the summary. So nanoparticles, as we have seen, can enhance the functionality of these hydrogels, making them an ideal candidate for cutting edge applications in wearable electronics and also the soft robotics. Now we have an arena of soft robotics. We are actually trying to develop the robots in a very, in a very resembling manner to a human being that can have hands like a mother touch. They can have the flexibility of a 25-year man. They can have the power of a 20-year boy in terms of strength. They can have high conductivity. They can sense. They can work in any environment ranging from some minus degree to around 48 degree. Okay, so we are actually progressing in this, and still there are certain challenges which are to be addressed. The foremost challenge is the scalability. That is, still the things are very, very expensive. Certain nanoparticles are very expensive. So incorporation of these and coming it in the on an scale is actually a problem. That is, we have to be very cost effective so that we can make it to general public. So the future outlook will be the biocompatibility, the sustainability, and the scalable hydrogels. So we have to address these issues, and hopefully after addressing these, we can have a better hydrogel which can be more fruitful to our humans, and that can actually change our lives. So in the end, I would like to acknowledge and also congratulate my research student Ariba Khayal, who meticulously reviewed the area of hydrogels and with regard to special regard to flexible electronics, and recently she has published her findings, her compilation in Journal of Cleaner Production with a very high impact of 9.8. So thank you all. Now it is open for discussion. Yes. Aditi, any online? So if you are not asking, then I will ask from myself. Yes. Actually, by piezoelectric, we mean to say that we have to harness that energy which is generated. So what we are actually intending to do is that we have to have a hydrogel which by movement, when the electricity is generated, that can store that electricity and that can be used for some other meaningful purposes. So that is the use of using the piezoelectric hydrogels. A similar case is when we are going to use that movements into the energy. Yes. 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 Yes, of course. Nanoparticles can be affected in a number of ways. You can have a seat. Nanoparticles can be affected in a number of ways because the properties of nanoparticle depend upon the type of synthetic protocol, its size, and of course the materials which are using. So the moment you change any one of them, the properties will change. Yes, of course, morphology will be affected first because the moment you change the size, the morphology will be changed. And moreover, nanoparticles, as I have said, that it is not always good. Although we know that silver nanoparticle is very beneficial for us, it has antibacterial action. But after a certain, after a certain concentration, it shows toxicity. And that study has already been reported that it becomes toxic. Even if you incorporate after a certain permissible limit, then the hydrogel will also become toxic. It will show negative effect. Yes. It is different for different materials. Yes. Actually, self-healing, what happens is, we have two type of crosslinks. We have the physical cross-linking and we have the chemical cross-linking. Now, for example, if you are going to stretch your polymer, if you are going to stretch your hydrogel, then it will stretch up to a certain limit, and after that it is going to distort and finally it will break. So this distortion and eventual breaking is actually, if you think in terms of the atomic scale, then actually you are lengthening your bonds and finally you are breaking your bonds. And initial stretching is because of the physical crosslink, but the eventual breaking is because of the breaking of the covalent bonds. So the moment each hydrogel has a permissible limit, that each hydrogel has a certain, certain length that can be stretched, and after that it can be broken. So that actually depends upon the type of bonding which is there, whether it is amide linkage, whether it is ester linkage. So each has a different stretching frequencies and each having a different bond energy. So the moment you came out that, the moment you increase, so at that point of time it will rupture. Yes, it is intrinsic property. It is intrinsic property because it is dependent upon the bonds. Yes. Actually, we have synthesized a hydrogen. We have synthesized a hydrogen, and what I've shown in the very first one. Yes, here it is. This is the hydrogel which we have synthesized in laboratory. You can see there, it is sticking on my palm. So, luckily or fortunately, whatever you want to say, is that we have synthesized a hydrogel and without using any additive. Of course, in some cases we need additives so that we can have a good sticking. We need good addition. But in this case, it was found that this was already having some inherent property that gives some sticking property. And you can see the angle of my hand. If it is non-sticky, then it may fall down like this, because this is 45-degree angle. So it is still there, it means it has some inherent addition. So otherwise, if do not have that addition, because in certain cases there is no addition, then we have to add one component for addition. Yes. Yes, because it is composed of biodegradable monomers. That's what we can at this time propose. Bec- No, actually, each hydrogel has a, working time, working life. For example, for this one, what we have seen is that it has a working life of around 1 month, and after that, it starts decoloring. That is, the moment it shows decoloring or moment it shows some patches, different color patches, then we can think that it starts degrading. So in our case, we have seen that it was stable up to 1 month, but there may be cases, I have not seen anyone, but there may be cases that this may not be so stable. So if it is not so stable, then we have to replace our monomers. Because if we want to make it compatible, if we want to make it for general public, then it must have a good lifetime, at least for a month. For example, if you have seen in my slides, it is purely an adsorption process. I have not talked about catalysis. It was a purely absorption process because we are more concerned with the absorption. We have not, utilized our hydrogels in terms of catalysis, because in catalysis the things becomes entirely different. So we have used it in terms of the dye absorption, just to ensure that it has a good absorption. Yes. Okay. So now let me go through this once again. Now you can see graphene and you can see chitosan, and you can see polypyrrole. These three things are entirely different. And luckily what we have found that our nanocomposite was found to be excellent in terms of its strength because of the GO. And it was biodegradable also because of the presence of chitosan, what we expect. And it was conducting because of the pyrrole. In most of the cases, we choose monomer depending upon the area, that which type of area, which type of problem we are going to address. In the later study, if you see that we have, since now we are more concerned with hydrogen. Earlier it was nanocomposite. When we were talking about nanocomposite, we were not talking about the human subject. But the moment we are switching over to humans, we have to make sure that it must be biocompatible. And at the same time, from environmental perspective, we have to make sure that it is biodegradable also. So you have to choose your monomers depending upon at what is your area of application and what is your problem which you want to address. So you have to take on this basis. Similarly, if you want addition, then you have to have some certain monomers. For example, you can use glycol because glycol has some inherent property of sticking, and at the same time it is also very safe on the skin. Glycol is generally used in burn cases, so it is very friendly to the skin. So depending upon your area and depending upon your need, you have to decide your monomers. Okay? Yes. The area is open for discussion.
We can have more discussions during the lunch time. It's almost 1 o'clock. We'll be starting the lunch. As today the lunch break is 1 p.m. to 2 p.m. and then we'll proceed to the Nanotechnology Center and UC.
Okay, thank you very much for your patience hearing.
A huge round of applause for very energetic central lecture.
Okay, thank you very much.
हाँ कहाँ पर हैं आप लोग? यहाँ नहीं आएंगे डायरेक्टली? यहाँ करा देंगे रिफ्रेश, बाथरूम वाले होंगे। अच्छा तुम भी वहीं हो? ओके ओके। सवा से डेढ़ के बीच में करते हैं। I am announcing the name of the students because we have divided student into two groups because of the limited space in the instrumentation facility. We cannot accommodate all of you. We cannot accommodate all of you. देखो उसमें आ रहा है YouTube में. So we have divided into two groups. In one of the group we have around 30 students. In the second group we have around 40 students. आप group 1 के साथ जाएंगे, ठीक है? Because we have to cover the whole demonstration process of the Raman as well as XRD schemes. Should I call the name? Group 1, where is group 2? Group 1, Adnan Hamid, Neelofar Irfan. Please note down that you are in group 1. Ruqayya Parveen, Kashfiya Rahman, Aisha Irfan, Muhammad Shadab, Adnan, Anam Fatma, Asiya Tariq, Adil Muhammad, रमी रमीज़ा एहसान, फिरदौस, रिफ़ा रिजवान, धर्मेंद्र सिंह, अदनान अहमद, शेख अनम सरफराज, विक्रमजीत सिंह, कृष्ण कुमार यादव, रूही सिद्दीकी, रमशा खान, फ़रहीन गयास, इबादुर रहमान, रमशा, सारा शफ़ीक, दानिया शाहिद, तौसीफ़ अहमद, सैफ़ अली ख़ान, जैद रेहान, सैफुर ज़फ़र and Sidra Shakil. You will be accompanied by Dr. Farasha and Dr. Asfar along with you. He will be coordinating your group and you will also be there. This is group 2 includes
Group 2 includes Laviza Bano, Wajiha Khan, Nazia Noor, Tasneem Firdaus, Abu Bakar Uddin Faruqi, Fatima Yashfin, Muhammad Mudassir, Muhammad Affan, Abdul Manan, Ayat Faisal, Adiba Zahir, Nahid Khanam, Muhammad Salim, Azhan Ahmad, Faizul Kamar, Wajiha Zuberi, Gania Mirza, Meha Kareem, Afia Nahid, Firdaus Yamin, Sadia Parveen, Alisha Mirza, Zoha Maqsood, Dania Ikram, Ikra Jamil, Suhaib Ansari, Sayyid Ali Waqas Ahmad, Zaim Ahmad Sherwani, Arfat Salman, Aisha Fatima, Tariq Abbas, Hiba Irfan, Saqib Hussain, and Tuba Fatima.
please go with your group. Do not change your group. So group 1 will proceed to Nanotechnology Center first and group 2 will proceed to USIF, University Sophisticated Instrumentation Facility. They will stay there for an hour or maybe 1.5 hour and then we'll change our positions. So INC people will come to the USIF and UC will go over there. 5 o'clock will disperse from there only. We don't return back. Okay, we won't return back here. We'll be meeting tomorrow morning then. We are starting the lunch shortly.
Any one of you want to submit your assignment? You can submit here.
Want to submit? Submit because you don't have to
And listen, we have a bus service here, so we go together. Okay?
INC people will come to USIF, while USIL people will go to the INC. There will be a number of equipments available in USIF. For example, we have LCMS over there, the liquid chromatography coupled with mass spectrometry. We have SEM, scanning electron microscopy. We also have transmission electron microscopy over there. We have confocal microscopy, confocal laser scanning microscopy, NMR, and even XRD, single crystal. So in USIF, you will be given the demonstration of Raman spectroscopy. While in the interdisciplinary nanotechnology center, you will, although there are a number of equipments over there, but you will be given the demonstration of XRD. XRD, X-ray diffractometry, is basically used to study the crystallinity of a material, the particle size, the geometry, the phase structure. What we generally do in X-ray diffractometry is that, just I want to give you a brief information before you go and see the equipment. X-ray diffraction. Basically, light is diffracted by different planes of a material. A material has different planes present in it. When the light is incident upon it, the light is diffracted. Diffract means turn hoti hai due to the sharp edges of the material. For example, if I ask you to throw a ball on the floor, even if you do not know whether the surface, this floor is smooth or it is rough, just because of the bouncing of the ball, you will realize whether the surface is smooth or rough. Even if it is dark all around, you cannot see the floor. Just by throwing the ball on the floor and noting down the angle by which the ball is rebouncing, you can determine whether the surface is smooth or rough. The same concept is utilized by shining the X-rays on the sample, and sample has different planes. Due to the sharp planes, X-ray bend, undergo diffraction at different angles. We measure those angles and apply the equation in lambda is equal to 2d sine theta. And we measure the theta first of all and put in that equation and calculate, and lambda is also known, the wavelength of the X-ray. We can calculate the interplanar distance between the materials. If the material is very, very crystalline, as you all know that crystalline materials have very good structural arrangement. If I ask you when you enter the class, I give you enough time to sit accordingly, then this type of arrangement which I am seeing right now, it is a crystalline arrangement. The way you were standing for lunch, that was a type of amorphous arrangement where there is no regular pattern, no regular order. Similarly, depending upon the nature of the material, if the material is crystalline, the layers are properly arranged, we got sharp angles and sharp peaks. Those sharp peaks reflect that the material is crystalline, and from those sharp peaks we can also calculate the size of the crystal as well, known as crystallite size. And since we are doing this workshop, this GIAN course on nanotechnology, nanomaterials, for nanomaterials it is very important that once you prepare your material, you have to ensure and you have to prove that they are in nano range, and for that we have to do some analysis. So we use XRD for calculating the particle size of the nano particle, to show and to justify that what we have prepared, it is in the nano range. And through that test, along with the particle size, we also determine the structure, the morphology, the geometry. So XRD is used for that. Then we have Raman spectroscopy. This spectroscopy was developed by Sir C.V. Raman. We celebrate Science Day on his birthday. The Science Day we celebrate, it is celebrated on the birthday of C.V. Ramanji. And this technique is basically a complementary technique to FTIR. The molecules which do not show absorption in IR main criteria for a molecule to show to be active in IR, that criteria is dipole moment. Similarly, we have polarizability for Raman. If a molecule does not have a dipole moment, it is inactive in IR, but in that case, we can use Raman spectroscopy. So both IR and Raman are complementary. Both of these techniques are based on rotational as well as vibrational transitions. So the energy required for these types of transition are a little bit less as compared to UV. UV is called as electronic spectroscopy because it involves electronic transition. For electronic transition, we need large amount of energy, and therefore we use UV radiations which have shorter wavelength and higher energy. But for IR, we utilizes IR radiation. In case of Raman, the detector, in any of the spectroscopic technique, the two main components, the two main units of that spectroscopy equipment are the detector as well as the light source. So for Raman, we use laser, the light amplification for stimulated emission of radiation. That laser light is used as a light source, and charge coupled devices are used as detector. So these are the two main components of Raman spectrophotometer. On the other hand, we use X-rays. X-rays are generated when beta particles are being targeted on a soft material, then X-rays are emitted. Those X-rays are then fall upon the sample, they are diffracted, and we'll get the angles of diffraction. From there we get information relating to that. So these are the two basic techniques which we are going to see today. Demonstration will be given. The bus is standing outside. I think I have already covered. No point of showing the same which I have already covered. We are already late also. We have given 2 o'clock time to both those centers that will be there by 2 o'clock. So we'll be leaving right now. Clear? 1 to 30, group 1, along with you, with the camera. 31 to 68 in group 2. Please proceed. Dr. Farasha has already left for Nanotechnology Center. Asfar will also be going. आप दो लोग भी चले जाएं. वारिस